Assalamu alaikum, ladies and gentlemen, welcome back to another live stream. So this is the third part, I believe, of this series of me rewriting my C++ Vulkan engine in Rust. Alright, so let me share the stream on my Discord. Please join my Discord server. You can find the link down in the description below. So you can get notified, vote, and also talk to me directly. Alright, so live. And there we go. Okay. So I did some refactoring off stream. So like yesterday's stream was a very long debugging session of WSI problems, and that really kind of pissed me off. And so I just refactored everything into Volcano, which is like a safe Vulkan wrapper, which is honestly way better and solved a lot more problems than I thought it would. I mean, I knew about those before, but like I actually forgot about them completely. So let me show you what I've done so far. So right now we just have like 10 windows that are being colored using Vulkan, right? So just kind of like a rainbow color just for testing, right? So here of course we have an example clear color which uses our own library engine, which of course you could also use. It's in GitHub right now, pretty much. And yeah, so I'm basically just gonna go through all the changes I've done so far, and then we're gonna continue pretty much. All right, so let's see. So first of all, maybe let's start with the example clear color here and see. Okay, so I added a few things. So this is the old file here. Let me see, would this be easier? Unified viewer, yeah, maybe. Actually, all right, so basically, hello Mucho, welcome back to live stream. How's it going, man? All right, so I basically had, and by the way, this is what we got. I just refactored the Volcano pretty much. What do you guys think? Should I like ditch this and show you the whole refactor, or just continue and explain? What do you think? So basically what I have so far is just a little demo with a main window here. Where is it? A main window. Yeah, this one I believe. Yeah, so the red one is the main window, so I can't actually close it. I can't close it without closing its children, which is all these windows, as you can see here. But if I close these windows first, so this is something I also implemented, and then you could actually close the parent window. It's just something little, right? All right, let me show you. Let's see. So here I got an app. And I really modularized the hell out of it. And hello, Noah Honcho, welcome to live stream. Okay, so here we got a renderer, right? And we got windows, clear colors, start, and primary windows. So let me just explain the whole changes that I've done so far. Hey, I'm also learning Vulkan with Rust. What Vulkan creator are you using? Sammy Sensei. So in the first two streams, I was using Ash, which is like the raw and safe binding of Rust. And it was just too much crap that I have to handle myself, and it's really fiddly. Like you could easily shoot yourself in the foot, just like C++ and C. And now I refactored actually into Volcano, and it's fixed a lot of my problems, which I'm gonna show you what's the difference really in this stream. In fact, you could even go into GitHub, really go to my Git repo. Let me see, github.com. Let's see, where is it? Kodotaku Engine RS. Nice, I'm also using Volcano, that's great. So, Kodotaku Engine RS, right? And here is the previous, like if you go to commits, you can see all the live streams, right? So this is the code that we made in live stream 1. Then we kind of refactored a bit the project structure in livestream 2. Then we actually had some problems with the synchronization thanks to hash raw binding, right? And then finally what I have here is the third refactor to Volcano from Ash. All right, so let's see what we got here. So my app right now, this is the clear color example in my engine. Foolishness machine, foolishness. Hello pixelated, welcome to live stream. All right, so we got a render, we got Windows. So this is a Windows abstraction. I was calling it graphics before. And here we got clear colors, which is a hash map from window ID to a color. And then we got start option STD time instant. And then we got a primary window, option window ID. Here, this is phase from ID. All right, so here what we got. So in resumed, what I do is if let some, well, not graphics, I called it Windows now. So if let some Windows equal to self.windows as mutable, then we say resume, Windows resume. Here we basically make the driver. I kind of moved this code to the application code Y instead of the engine, so the user could actually make, choose the physical device himself that he want to use, the GPUs he want to use, and he can even use multiple GPUs. Like he could use some Windows with this particular GPU and the others with another GPU of their own choice, basically, and also the key family index, right? I mean, like if you want, let's say you have 2 GPUs on your system and you want some Windows to run on that GPU, then you could just like create another struct here called Windows 2, right? And it would just be like option Windows. Like, which you wouldn't find on any other engine, mostly. I noticed Vicky config GUI only starts working for me after I interact with at least one widget of the group that's broken. Yeah, I'm not sure. Especially in Wayland, debugging tools kind of sucks. So no messages. I need to turn off warnings and turn them on and it works. Yeah, I also had some bugs with that. Either way, here we're creating the driver, which is basically just like loading the Vulkan DLL essentially, and loading some other stuff like the instance. Here we choose a device. We have this convenient function called request devices like WGPU. By the way, one thing I wanted to cover, which is what's the difference between WGPU and Volcano? Because the thing is, after I moved on from Ash, which is the raw binding of Vulkan, I had 2 choices that are safe graphics APIs. I either had Volcano or I had like, what is it called? WGPU. So the difference is that WGPU is actually cross-platform. It could even work on the web and it have its own kind of like dedicated Metal API. And Volcano doesn't work on web, of course. That's first. Second, Metal API, you need to go through Molten VK layer. Translation layer to Metal, but it actually does works on Mac too, and it also works on Android too. So basically almost all platforms except for web, WGPU could do that. And honestly, if we really need web, we could probably just make a new backend for web, like using WebGL, or I don't know. Either way, the other problem with WGPU, why I didn't pick it, is it's not very ergonomic compared to Volcano. You're gonna see Volcano gives us a lot of cool stuff like compiling at build time, compiling shaders and giving me errors inline. First of all. Second of all, it gives me reflection of shaders, so I don't have to write the vertex layout and the descriptor layout and all that crap. It just infers it for me, which is very convenient, especially since we're starting out. Later on, I probably want to do my own runtime shader compilation using Shaders or something. But for now, we're just gonna start with that. Now, what I was actually basically wanting to do with the raw binding is that I wanted to use those modern extensions just so I could remove this pain point of actually defining these myself. But now Volcano, and especially even in synchronization, but Volcano actually handles all this for me using reflection and using it handles synchronization for me, so I don't need synchronization to extension either. Though we're gonna use dynamic rendering, that's for sure. That's the only thing that we're gonna use, the only extension, at least for now. Though maybe later on we're gonna use bindless, I'm not sure. The other thing with Volcano that is way better than WGPU is that your buffers, your GPU buffers in WGPU, they're not typed, right? So they don't have a type. It's like just bytes essentially. That's the first. Second thing is that since WGPU is like targeting the lowest common denominator of the platforms it supports, which is basically web, you have a lot of arbitrary limits that doesn't really exist in desktop, but you have to handle them because you are targeting web 2, like some extra alignment for no reason, and you have to do a lot of extra copies for no reason, is at least in desktop, because you're targeting web 2, which really sucks. And you also have to handle what is it called, alignments and all that crap. So I just wanted to tell you about that. The other thing also is that you can't use like modern Vulkan extensions like you can in Volcano. Like for example, you can't use ray tracing in WGPU. You can't use mesh shaders. I think compute shaders probably quite limited compared to, well, native, right? And you have to write WGSL. Either way, I think for now I'd stick with Volcano. Maybe later on we could even make another backend if we really need to, though right now I'm not really gonna bother. So that's pretty much it. I just want to make sure that I make that clear on why I made that decision. Other than that, so let's go back into what we have here. So here we request a device from the driver. Otherwise, if you really want to choose a device yourself, you could say driver dot enumerate physical devices. So I have basically two functions for the user to choose from. Request devices inspired from WGPU. You kind of have something like this. Also, another thing that I just remembered about WGPU is that it has some async functions because of web, which really sucks. You have to like add some blocks or crap and so on. And yeah, either way, Volcano is like the best graphics API I can find. Not even in, you can't even find that in C++. Like in C++, the closest you can find for Volcano is Daxa. So Daxa is like the closest you can find to Volcano in C++ land, right? Otherwise, you just have to write like raw Vulkan or go straight into some big engine or framework. And yeah, so this is the closest if you're interested into C++, so that's something you could look at. It's quite interesting. But yeah, alright, so what's about using allocator for this project like VMA? Okay, so another cool thing about Volcano, it actually comes with its own allocators, so we don't need VMA, we don't need any of that crap. In fact, it's even way better than VMA, at least in terms of choice. Like you have way more choices, and it's more integrated into the API essentially of Volcano, which is pretty cool. You're gonna see that. It's really amazing. The other thing too with Volcano compared to raw Vulkan is that it is thread safe. Thread safe, first of all. It's like the thread safety is encoded, of course, in the type system, right? And of course, you can't have like a null handle. Like if you want a null handle, like in C++, null PTR, or in row binding, you say, fence null, for example. No, that's not possible here. The other thing is that everything is an arc, so, well, thread safety. The allocators are also thread safe. Which is great. The other thing is that it destroys the objects once they go out of scope, right? And it makes sure that the objects lives as long as their parents using args. So like there's a whole bunch of cool ergonomic stuff with Volcano. It's amazing. I actually forgot about all these features. I'm not sure why I switched off from Volcano. I probably got distracted before with some other weird thing like creating a programming language or something. I don't remember. Either way, Daxa is better than OpenGL. Daxa is basically just C++ abstraction over Vulkan. It's also using like modern extensions. It's the closest you can find to Volcano, and honestly you may want to give it a shot. Like if you want to write Vulkan code in C++, then maybe give it a shot. Like the raw Vulkan stuff is really, it's not even doing something interesting. Like it's mostly just API idiosyncrasies and boilerplate code. So really these little wrappers really makes our job way easier. Alright, so let's go further. So here we're creating a GPU from our driver, of course, and with our physical device that we chose and the key family index. Here the driver just choose, like the engine just choose for us something that you're gonna see later on what I do. And here we got the windows. So this is just a little abstraction over my engine core types, which you basically give it a GPU, and yeah. Now what you could do is here I'm creating a primary window, which is just a window ID. It's not the actual window. The actual window is actually stored inside Windows, as you're gonna see later on. And here you just call add and you give it the event loop, right, that we got from winit, and then you give it window attributes like the title of the window, etc., size, etc., etc. And yeah, that's pretty much it, and it returns for you the window ID so you can refer to it. And then here I have just this clear colors extra. This is just some way to show you how you could use those Windows IDs. So one way you could use them, for example, to store things for that window. Like here I got a hash map from window ID to a color, right? I called it clear colors. And basically I say self.clearColors, insert primary window and the clear color I want. So here for the primary window, I'm making it red, right? Next up, I'm creating 10 windows here. I'm creating 10 windows, so I'm saying windows.add, just like here. I'm giving it the event loop, and then, you know, the window attributes, I'm just making it default. So here, one pattern I want you to notice here is that instead of saying window attributes or any other kind of structs default, like if you don't want to type the exact type, you could just say default, and it would just infer the type basically. So here it's window attributes. This would basically you know, kind of resolve to window attributes and in fact you could do this with any other kind of trait. Like you could just use the trait itself and it would infer the type for you, which is nice. So the other thing here, I'm just like calculating a little color thing here. So I as f32 divided by 10, so I just get a different color for each. Here we got self colors, insert window and a color, and here I'm adding as child. So I'm adding this window that we just created as a child of primary window, right? That's kind of like the mechanism that I've added where like you can't actually close the main window, like a parent window, except if you close its children, right? So let me find the main window here. Here we go. This is the main window, which is red. I can't close it until I close all the children. And it's just a little tree just to show you that how it is possible kind of using window IDs without like going into the borrow checker problems, since we're not using pointers or references, which is great. It's also way safer either way. So self.windows, some windows, render. So here we just kind of like put our stuff there, and here we just have like start is equal to time instant now. So we just like register the current time instant. Doxa is, oh yeah. All right, so next up, here we got the window event. Here I'm just taking a reference to the windows and renderer, right? And I'm matching on the event. So if we have a close requested event, I basically made a function in that Windows abstraction called canClose, right? And you say if that window can close, right? Here we're referring using the window ID, as you can see. Now, if that's the case, we're gonna remove the window, and if there is no windows left, windows.length is equal 0, then we're gonna exit the application. Right here, you could do all sorts of cool things depending on what you want. You could either like, if any window gets closed, you could just close the whole application immediately. You could do all sorts of other logic depending on your application use case. So that's cool. Next up, we have redraw requested here. So redraw requested, you say windows.redraw. You give it which window should redraw, which is window ID, right? The renderer, and then the clear color in the render params. Well, today we get a full screen quadrant shader. Of course, yeah, we're gonna get a shader today for sure. Finally, Volcano would really helps us do that very quick. Without having to bother with a lot of crap. But either way, here we got render params. I made it a struct so we could easily like extend it later on once we make our render bigger and so on. So here just clear colors, self.clearColors, and here we're using the window ID as the key to the hash map. Cool. And in wrap, that's pretty much it. Now resize, you just say windows.resize window ID. So about to wait. Here, about to wait basically triggers when we don't have any other window events to actually process. So if we don't have any redraws anymore, no close requested, no like events like, so basically if we handle all the window events and we don't have anything to do, then we're gonna try to update and then request redraw again. How are you doing that cursor size change? It just came with KDE. Like when I actually move that real quick, it just like do that. So yeah, so here we got elapsed. So we just calculate the elapsed time from the start of the application. Because if you remember here, we set the time to instant now here once the application started. And here we could take how much time have elapsed since then. So self.start in wrap elapsed as seconds f64. F32, and then here the speed hertz. This is just a bit of little math that I'm also gonna explain, just in case if you're not that great with math. Very simply, I'm not gonna show you any crazy equations here. Either way, so self.clear colors, we go iterate mutably through every color, so we could like change those colors, and we filter here. Notice we filter the ID. We basically filter any windows that is primary window, right? So we don't want to update the color of the primary window, because I just want it to keep its original color, which is red. That's why I'm filtering it out here. If I don't want that, if I want the primary window to also have that, the nice thing about iterators, they're composable. I could just remove this line and you're good. You're done. So that would happen. Great. Other than that, here we go in for each window ID and the color. So here we got a mutable reference, which means we can change it. So as you can see here, we're saying the reference RGBA equal to this. So here we got red, green, blue, all of them like from 0 to 1. Now let me try to explain this weird thing that probably a lot of you wouldn't understand. I mean, well, it depends, right? So here we got a hue number, and here I have this little function phase from ID. What you gotta know for now about phase from ID is that it just takes this ID, right, this window ID, and it converts it into a number, so we could basically have a different color for each window, right? Because if we don't have this kind of term right here added into the phase, what's gonna happen is that all the windows would have the actual same color, as you're gonna notice it, because there's no variable that would change from one window to the other, right? That's why we just add this, so basically the color would change from one window to another. And this basically, so the window ID is kind of like an opaque type, right? It's not an actual number, it depends on the platform. So what we do here, we just hash it, right? So we say we create a default hasher, then we hash the ID, right? Because window ID does implement hash trait. And then we do this little trick just to make sure it's pseudo random but also deterministic. You don't really have to bother with this. In fact, you don't even need to do it either way. And finally, we get a number from 0 to 1. Of course, a float basically for this particular ID. Who doesn't know what phase is? I mean, there's a lot of people that aren't really, you know, that literate in math, you know, so I'm just gonna try to like explain it my own way. All right, cool. Let's see. So now where we were. Okay, so we got this hue, which is basically this phase number that is unique for each window. Then we got plus elapsed times speed hertz. So this is the time. If we didn't have this elapsed time, if we didn't depend on time, then this wouldn't animate. Of course, like if this was just 0, this wouldn't animate because we're not dependent on time. Yeah, look at that. It doesn't animate since we're not dependent on time. Other than that, we have this speed hertz just to basically control the speed. Like we have 1 cycles per second, right? 1 cycles per second. If you want like to be faster, you could increase that and so on. Either way, here we have rem, Euclid, so we just get like the remainder by 1 either way. Now here we just got like this this thing right here, right? So red, green, and blue. It's also kind of phased, so tau times hue plus 1 divided by 3. So let me show you a little program that I could show you what's going on there real quick. which was very useful to me because I'm also not very good at like algebra, so I'm very like a graphical person, right? So I'm just gonna share this little program real quick. If someone would find it useful that is struggling with these kind of equations and so on. So here we got tau, which is basically pi times 2, and I believe we have it here too, times u plus 0. Well, here sine, right? Let's say sine, and multiply add. But let me just show you real quick here what's going on. So this is basically, well, this should be x, right? And here we got like tau times sine x plus, let's say, pi divided by 2, I guess, or something. Let's see, wait. Or honestly, let's remove this stuff. Let me just show you conceptually what's going on here. So here we basically add this phase right here, this guy right here, this A, let's say, to actually change the phase. Otherwise, all the windows would have the same color basically. Yeah, let's not overcomplicate it, but this is just a little program that I wanted to show you real quick. Either way, let's not waste more time on this. This is becoming a math class. Alright, so self-suspended. Self.windows as mute in wrap suspend. So this suspend would basically make sure that all the renders get destroyed for Android to work, basically. And yeah. And that's basically the clear color example, nothing crazy. And it's all using Vulkan under the hood. Right now, let me show you the actual engine code. The engine code. So here we got lib.rs, which basically have a public module core and public module graphics, which means that core and graphics right now are actually visible to the application to use. And core basically have all the stuff that doesn't depend on a specific library, like it only depends on Volcano, right? It doesn't depend, let's say, on Winit. And we have this little graphics folder which basically builds a little abstraction helper on top of the core types, right? I mean, in your application you could build on top of the core directly if you don't want to use the helper. Now let me show you the helper first, I guess. So the helper, here we go, the graphics, it should be called Windows really, because I basically renamed it. Windows. Okay, so Windows, we actually had this some of this logic in the application itself, and I kind of abstracted it away. But you could always, you know, go down and use the core types. Because you push the Volcano changes to get. Yes, I'm gonna do that in a second. So, alright, so here we got a GP, we got the GP, hello GP, welcome to live stream. GPU, okay. So we got the GPU and we got Windows, so hash map window ID to an arc window. So we're basically storing all the windows here, and we're storing the swap chain targets. So the swap chain targets is interesting. I was calling this renderer, but you're gonna see why I actually renamed this to swap chain target later on. And here we just storing another hash map called children, which have a window ID and a vector of window IDs. So basically for each window we store a vector of children of windows, right? Of course, we're not storing the actual windows themselves. It can get really nasty really quick, so we're just using the window IDs here. Other than that, honestly, this should go really with the other guys. Let's just put it. So yeah, just instead of like you having to, like the application having to do all this logic for no reason, I did it myself. Right, so here we got the new function. It takes a GPU and it creates some empty hash maps. Pretty simple. Next up we have the add function that we use to actually add windows. So this is what it do. It takes the event loop and the window attributes, right? And it basically creates a new window using the event loop, and it passes it the window attributes we got from the user. And it wraps it in an arc. And then we create a renderer. Actually, this should be called swap chain target, because I renamed it. Swap chain target. Okay. So we create a swap chain target. We give it the GPU and we give it the window. And the window size. That's pretty much it. So like the extent, the width and the height. And here we take the ID of the window and we insert in the window in that ID, and we also insert the swap chain target in that hash map. And we return to the user the ID that we used to identify the window. Next up, we have a remove function. So we remove the window, we remove the swap chain target. They will automatically get destroyed once they get removed. And then we check if we have some children. Is learning WGPU Rust a good starting point in learning GPU programming? Start studying it last week. WGPU is also a very solid way of doing it. So go on. Yeah, continue. WGPU is very solid. I recommend it. You have Volcano and WGPU. These are pretty good. Pretty amazing APIs for modern graphics. So let's go. All right. So if let's some children, self.children remove. So we remove the child. We remove the child. And we go through all of them and we remove them. We remove the children of that window too, basically. Next up we have add child. If we find some children, then we basically push that child. Wait, what the heck? We add child. Vulkan, I use Visual Studio 2010 on DirectX 9. Hello Polar, hello Internal Scripture, welcome all to live streams. Vulkan, I use Vulkan's Visual Studio 2010 on DirectX 9. I just understood what you meant. Nice to meet you, seems, yeah, alright. So here we have add child. We check to make sure that there is some children already. If there is, then we just push the child, the new child, into that list. If there is nothing, we actually insert a new entry into the children, because here basically I have you only pay for what you use, right? So if you don't care about like the parent-child relationship of Windows, you don't, this wouldn't allocate and it wouldn't be used, you know, until you actually use that functionality for some window. Then it would actually create a new entry for that. If it's already existing, then we just push the child, right? Here remove child, so just check if there's children there in that parent, and we retain any window that is not equal to the child. And then if children is empty, then we just remove the parent from the children, the parent's ID, right? Here get can close. The can close function basically checks if that window have any children. If there's any children, then it would return false, meaning it can't be closed. Otherwise, it returns true. And then here the draw function, it basically goes ahead and takes the swap chain target of that specific ID, and it takes also the window. And here it checks if there is some acquired, meaning we actually was allowed to get like an image and frame this time, because it could be that maybe the window is like zero sized or some problem happens, so we don't get it. So if we do succeed in trying to acquire the image, and we also pass in, by the way, the size here, then we create a command buffer using a renderer here. So render.render, and then here we pass the acquired image that we got from this try acquire image, right? And the render parameters we got from the user. After that, we basically present the acquired frame with the command buffer that we got from the render. So here I'm kind of separated a few things here. So before we have the one render which did presentation, did rendering, did like acquiring, did everything. Here I kind of separated them. We have now a swap chain target and a render. The swap chain target's job is to just get the frame, try to acquire the frame, and then its job also is to present the frame. And here you got like a separate renderer class which doesn't care if you're rendering to a window or rendering to an image, an offline image or whatever. It doesn't really care. Its only job is you give it some image, doesn't matter what the image is, and you give it some render params, and it gives you back a command buffer, a command list that you could submit to the GPU. And here we basically give it to the swap chain target, so it would basically use it on our window, essentially. Alright, bro is rewriting Windows.h in Rust, I think. kind of, but in a cross-platform manner, I guess. And also with like hardware rendering, right? Anyways, request redraw. So for every window, we just request redraw, and that's basically it here. Insert. Okay, so nothing crazy here. Now let's check the other ones that we've done so far. So we got the GPU. Let's start with the driver. So first of all, I removed the DirectX. Can I have hardware rendering? DirectX is more than Vulkan. Like, it's more code than Vulkan, first of all. And second, it's not cross-platform. It only works on Windows and Xbox. And third, I really hate those names that Win32 just... Those really sucky names, I don't know. Either way. Let's see what we got here. Wait, DirectX is more verbose than Vulkan? I mean, yes and no. Yes and no. So DirectX is less verbose in some few cases, like for example the swap chain stuff, because it doesn't care about cross-platform. But it have way worse names, in my opinion. And it could be way better since it's not cross-platform, you know. So, yeah. Either way, here we got driver. So create instance, arc instance. So right now, as you can see, we're not storing like ash instance and all that crap. We're only storing the instance here. So this is how you do it in Volcano. You just create a library. So Vulkan library new, and I just pass it directly. I don't have to store it because this is an arc. It like the instance would make sure that the Vulkan library would live as long as the instance because it's taking an arc, right? So I don't really have to store it to extend its lifetime essentially. Volcano would make sure to do that for me. Enumerate portability. This flag is needed for Mac OS support, basically. But yeah, the next thing is we have enabled extensions. We get the required extensions of the surface. And next up we got enumerate physical devices. Nothing fancy, it just uses the enumerate physical device from Volcano here. Create surface, same thing, surface from window, blah blah. Nothing crazy. Here this param, I just took it from the signature of Volcano, you know, just copy and paste this. Pretty much, nothing crazy there. I didn't want to depend, so basically we are doing this to not depend on Winit in the core module, right, of our engine. So like you could use it either with Winit, GFW, SDL doesn't really matter to the engine, right? So here we got create device. Okay, so here we pass in the physical device we're interested in, the key family index. All right, cool. And here we say device new. Right, we just give it the physical device and then the queue create infos. Here, we just give it one queue family index. We could create like multiple queues, but we're not doing that here. And we just say .defaults, meaning like any other stuff, any other properties, just, you know, set them to the default values. Next up, we have enabled extensions. We're only enabling KHR swap chain for now. And the enabled features, we're only enabling dynamic rendering. By the way, Vulkan will actually try to use like the latest Vulkan API basically that is available to the system, and it would handle automatically the dynamic rendering extension of Vulkan function pointers loading for us, so we don't have to deal with that either. So that's amazing. And here we just return, so when you create like a new device, it automatically returns for you also all the queues you requested basically, so you don't have to do it separately. And this is what we're doing here essentially, and here I'm actually just returning the result of Volcano directly, though maybe later on we gotta use the this error crate to make our own errors, but for now this should be fine. Next up, here we got request device. Request device, this is just a little thing. You could totally ignore it, like you could just go straight off and just say enumerate physical device, take the first one pretty much. Here we got the device extensions we need, right? And let me just go through it basically. So here we're filtering the physical devices. We're only taking the physical devices that got Vulkan 1.3 because we need dynamic rendering. And right, so if we have multiple GPUs, we only take the ones that have version 1.3 or more. it's nice and explained, but any resource start from that you recommend? Polar. Depends on what you want exactly to start off. Is it like graphics program in general, Vulkan exactly, and in which language? Rust, C++, and in which like you want to use the raw binding or Volcano like I'm doing here, or what? Either way, so Vulkan version 1.3 or supported extensions is KHR dynamic render, either one of these. So if it's less than Vulkan 1.3, then at least it should support the extension, right? Otherwise, here we also filter on that it should contain these device extensions we need, which is the KHR swap chain here. And here we filter map. So we go through every physical device, we list the Q family properties that that device has. We enumerate them, basically we add an index here, and then we use this position function here, which searches for an element in an iterator returning its index, right? So basically if we return true to any of these iterations, it would return the index we got. So here Q flags, we check to make sure that this Q right here, this Q family supports graphics operations, and it supports presentation to this display. If it does, then great, we're gonna take that and we're gonna map it to ISD32. Great. Next up, we just kind of like order the physical devices we got by the by a score, right? So if discrete GPU, we just give it. So basically, we're preferring discrete GPUs first, then integrated GPUs, then virtual GPU, then CPU, then other, etc. So just for performance reasons. So like if the user have, let's say, an integrated graphics card and discrete one, we're gonna prefer the discrete one. And that's basically, we take it from the properties here, the properties.device type. There's a lot of other properties you could check out that you could like use to basically do all sorts of cool stuff, but yeah. So yeah, that's basically it for the driver. Next up is the GPU abstraction. Yeah, I'm looking for resource for Vulkan binding with Rust as well. I'm super new to GPU in general, just want you to have a specific direction first. I'd recommend Volcano. They do have a tutorial. I haven't read it for a while. So Volcano Rust. So wait, I'm pretty sure they have a tutorial. Yeah, this is the one. I haven't read it since a very long while, so maybe you could try this out. That's the first thing. If you just want like regular Vulkan stuff, that you could check out Wiki Guide and Vulkan tutorial, but these are like using C++. But yeah, try this first. Try this Volcano like official guide and see how it goes. Or just like read their own examples even afterwards. So like if you go to Volcano GitHub, right? Let's see, does it erupt? Don't worry, welcome to the live stream. I'm not sure. What do you think? Alright, so here we got some examples. Just make sure, one thing that always trips me off is that make sure you go to the tags and you select the version that you're using, right? That you're gonna see in your cargo toml. So in my case, I'm using 0.35.2, so I gotta make sure that this is 0.35. Otherwise, you're gonna be seeing master, which is the latest version, which could be different. And that's basically it. I blue screened my computer with Vulkan once. It does erupt. Alright, so let's go back. What we have here. Things going good on porting. Yeah, we had a lot of problems last live stream with the raw binding. It's not really about Rust. It's just like Vulkan. Vulkan being Vulkan with some new validation messages and such. And me being me trying to fix it, which is something new on stream. But of course that didn't go well. But at least people got like a very good masterclass in debugging. But yeah. Alright, so let's see what we got here. And right now I just kind of like basically refactored it, off screen. I refactored it off screen, and right now I'm just like from Ash to Volcano, which is the safe Rust binding of Vulkan. And right now I'm just going through the changes I've done really quickly. to tell you guys how did it, like, what's going on, right? So I basically have covered the driver, and that's pretty much it. Now the GPU. And notice, by the way, well, we're gonna see about that actually. Anyways, so here we got the GPU. Let's see. So here we're taking the driver, we're taking the physical device and the key family index, and we're making some stuff. Okay, so here I'm just, you know, cloning the arc so it doesn't, the borrow checker doesn't tell me some crap, right? Here we're using the volcano function create device to create a device out of the physical device and key family index that the user have chose. Then we take the first queue out of there, because you could do multiple queues, which we're not gonna bother with right now. We're not that advanced, not that autistic. All right, so memory allocator. We're creating a new standard memory allocator for this device. So as I said, in Vulkan, raw Vulkan, you are on your own in terms of allocations. Most people, like most beginners, just like allocate stuff for everything, which is not great. You're basically making a whole allocation for every single resource, which is not great. But in Volcano, we have these memory allocators, which basically helps us efficiently allocate GPU memory, right? And the work for actually allocating and calculating all the alignments and all the other crap is done for us by Volcano, which is like, you know, people that have been doing this like for years now. We can definitely not beat them. All right, so, and also another thing, I believe it also handles threading and like multiple key families and other crap that you don't have to worry about since we're using Volcano. The same thing with command buffers. We are making a standard command buffer allocator here. We're just passing it the device and defaults. And that's pretty much it. Nothing fancy there. The next thing here, we just create surface. We just delegate that to the driver. And then we have create swap chain. So create swap chain takes a surface and an image extension and image usage, and it just basically takes the surface capabilities as we've done before. It lists the physical device formats and makes sure, wait, what did I do here? Oh yeah, here we take basically the surface format. Yeah, we take the first one. Yeah. All right, cool. Next step, we create a swap chain. We give it the queue and the surface, and then here we got a swap chain create info. We give it the minimum image count, the composite alpha and such, and yeah, that's basically it. We just create that, nothing crazy. Here we get this sync now. So instead of like creating the semaphores and fences, Volcano actually does that for us, but instead we have this weird GPU feature that I didn't really understand well so far, but we don't have to, since I already abstracted all that code anyways from the examples. And we don't really have to think about it right now. So most of this is just boilerplate code, really. So here, create command buffer builder. We just creating command buffer builder. So that's the GPU. And we actually removed a lot of the other helper functions that were inside the GPU because, well, basically, Volcano already, you know, exposed that for us in a very convenient way through its object. So no need. Next up, we got render. Oh, well, we got swap chain target and render. Render is very simple actually right now because of all those abstractions. It's very simple. So we just have render params, currently just clear color, though later on this is going to be more. And it only stores the GPU, right? And they only have one function for now, which is render. You give it some image. It doesn't really care if that image is coming from the swap chain for the window, or it's coming from, let's say, an image decoded from a FFmpeg video or whatever, or some other weird way. It doesn't really care. Just give me an image and give me render params. I'm gonna do the job for you. So here we're creating a command buffer, right? And here we're clearing, we have one command currently sent to the GPU, which is clear color image. Of course, this would change in this video because we're going to be using graphics and shaders and so on in a second. But right now, we're just clearing that image, nothing crazy. With the clear color we got from render params, and we're building the command buffer. So this is kind of like the builder pattern that we actually have done. So if you recall in the previous live stream, we had like a command encoder class I removed that because we don't need it anymore, because like Volcano have a similar thing. It's like here you could actually basically chain multiple Vulkan commands like this, right? It's just like what we had before in the command encoder class that we made ourselves, which is great. The other thing is that Volcano, we don't have to do those pipeline barriers crap, because like that's handled also by Volcano, which is amazing. That's just boilerplate code. And here we just build a command buffer, we turn the command buffer. Perfect. Now let's go to the swap chain target. Now this is the really the really weird part, because this is like where the swap chain BS comes in, right? So, but the nice thing is that it's very, I basically kind of like made it in this one file, so if we ever need to change it, like one of us would go down, right, and just go to that file and and fix it. Nobody else would have to enter this weird thing, right? Right, so we're only gonna bother with the render after that. All right, let me just go through it really quickly here. So we got the swap chain target, and we have recreate swap chain previous frame end, which is like a box dynamic, so basically dynamic dispatch for a GPU feature. We got the swap chain images, the swap chain, and the GPU. Now here we create one by basically taking a GPU and a window and an extent. Here we create a surface for the window, and then we create a swap chain. Notice that creating a swap chain in Volcano is way simpler than raw Vulkan. So it gives you directly the swap chain and the swap chain images. Here currently we're only using transfer DST, since we're only using transfer command. Sorry, but later on we're gonna actually use graphics, and we're gonna change this to a color. Like image usage, but either way. So here we take the previous frame int, GPU now, future. You don't have to really care about this. Either way. Here we got try acquire image. So this is the try acquire image that we were using to try to acquire an image, right? Nothing crazy. Here we check to make sure that this is not 0. If it's 0, then we just return okay, none. So yeah, everything went well, but we didn't get any frame this time because the window is basically 0 size. And next thing is self.previous, otherwise it would crash. So if we didn't do this. So here's self.previous end as mutable in wrap cleanup finish. Now the thing is, I told you that basically Volcano handles a lot of command pools and like synchronization objects, fences, semaphores, and stuff for us. Here we basically tell it to clean up after itself, right? Just so it doesn't like keep on making memory for it. Walaikum salam, and welcome to the live stream. Here, if we need to recreate swap chain, well, we're basically going to recreate the swap chain. There's this convenient recreate function in Volcano called recreate, and basically you just give it the new image extent. And here's a little Volcano tip, which is basically every single Volcano object stores also its own create info that you use to create it with. So what we do here using this little Rust syntax is that basically we only change the image extent, and we use the original create info that we used in the beginning to create the swap chain. We use it for all to initialize all the other fields, kind of like default. So you usually have default here, but we don't want default. We want like the original swap chain create info struct. That's basically it. Next up here we got acquire next image, blah blah blah. Just some weird swap chain crap here. If it's suboptimal, then we just flag it for recreation, but we don't recreate it just yet. Next up we say, and we return this acquired struct. So at first how I designed this, by the way, is that I had these image index and acquire feature, I had it stored here globally, right, in this struct, right? But then I changed it. Why? So basically I kind of enforced that the user would, I made sure that the user would call acquire image before he can call present by using this acquired struct. Otherwise, if I did that, like if I stored those fields directly, he could call without calling like try acquire image, he could call present. So this would basically make sure he does, first of all, call try acquire image to get an acquired object. Then he could pass it to this present. So kind of like just encoding the guarantees really quickly here. And that's basically it. So the acquired basically contains the image, the swap chain image we want to render to, the image index, and the acquire future. And here the present function, when you want to present, you give it back that acquired token that you got from this acquire image. And you do some weird crap again. As I said, you don't have to worry about this anymore, right? Just boilerplate crap. So here, self.previous frame end, we take it from the option, we unwrap it, then we join it with another guy, so acquired, acquire future. So basically, we kind of join the previous frame end with the acquire future, and then we execute after that the command buffer on the queue. Then we swap chain present. So we got the queue here and we tell it which image index, and then we signal and flush. And so basically Volcano would signal and flush for us. And here it would basically wait for the command buffer to finish execution. So as you can see, signal offense after this future returns another future that represents the signal. The nice thing also about this futures is that you could actually use it in async. So that's cool. Alright, and here just some error validation crap, and here resize, it just sets recreate swap chain to true. Alright, so the good news is we don't have to touch this anymore. It's just done, right? So all the swap chain crap is right here. We only have to bother with render hopefully from now on, which is great. Is there anything else that I didn't cover? Yeah, I think I'm pretty much covered all the changes at this point. I'm gonna push these changes. So Ash to Volcano refactor. And of course cargo toml. I just removed Ash and Ash window and added Volcano here. And that's pretty much it, nothing else. Nothing crazy. So let's commit and push. Oh boy, what the heck? Push. And now we can get to actual fun stuff. I finally have finished, like, how much that took. Oh my god, 1 hour to just explain the reactor. Oh my god. Alright, so let me see if that got committed. Yeah, so right now if you go to my repo, you can find the new changes, all the changes there. If you're following along, you could just come here, Ash to Volcano refactor, and you could see the whole changes one by one that I've done, essentially. Alright, that's pretty cool. So pretty much what let me see, wait. So plus 840 lines, I guess, and minus 759 for the refactor. Okay. Alright, now let's actually get to some fun stuff, which is shaders and actual graphics. Not just clearing the windows on the screen and juggling windows. Alright, so let's see what we're gonna do here. So we're gonna actually go to the examples of Volcano, because I'm not very familiar with the Volcano API really. And in fact, you're probably gonna copy most of it really. So we could focus on some more cool stuff. Like I'm thinking about basically making a UI library, since we just made a multi-GPU and multi-window kind of abstraction here, which works with Vulkan. So we'd better exploit that, I guess. But let's see. So the thing is here in the examples, by the way, first of all, make sure that tag is right, that version is right. The second thing is we have here two triangles. We have triangle, this one, right? And we have triangle V13. So this one is using dynamic rendering, right? And Vulkan 1.3. This one is not. This one is using render passes. So the one with render passes, let's see how much lines of code is that. It is 782 lines of code, and it would be even more for more advanced cases. But the other one, the triangle V13, let's see if it's any different. Actually, it's not that different, interestingly. Weird. Or maybe the comments is more. Yeah, there's the comments. Maybe that's why. Alright, so now let's check out this example. So currently we're just clearing the window. Cool. Next up, what we're gonna need. Let's see. So we have done all of this crap. So the thing that we're gonna need is some vertices buffers. Right, some vertex buffer, and then what else? We also gotta create the image views of the swap chain, because we're gonna render right now. So it's in window size dependent setup. And what else? The next step is to create the shaders. Okay, so basically Volcano have a very convenient macro for us to compile shaders and reflect them. And this is basically what we're gonna do here, really. You just say the type of the shader, which is vertex in this case, and then you type in the code of the shader. And that's basically it. Next step, you could create the pipeline. Right, and notice here that like using reflection, it actually automatically generate the vertex input for you. Otherwise, like from the shaders, otherwise you would have to actually write in the formats like explicitly, which we would have to if we were doing raw Vulkan binding. Or if we did our own reflection, which is even crazier, or vertex pooling using buffer device address extension, the other stuff. Either way, MD explains, welcome to lunch. So you tell me that you're writing a C++ Vulkan engine in Rust for real? What the heck are you talking about? No, it's like I started this as a C++ engine, right? And then I'm rewriting this in Rust, essentially. Okay, so pipeline descriptor, set layout, create info. Viewport. I thought I lost your buffers. I'm not sure how did you understand that. Like what? How you would write a C++ Vulkan engine in Rust? Yes, and write a shader parts on top of it to assert that your vertex and instance attribute match the vertex and alright, let's see. Recreate swap chain, attachment. Builder, begin render. Here it's using dynamic render, apparently. It's using that instead of render passes, which is great. And here we got the window size dependent setup. So honestly, I'm gonna copy a lot of this stuff so we could get two more interesting problems, really. And I'm gonna explain what's going on as I go ahead. Alright, so first of all, let's take this part right here. And the good question though is where we're gonna put this. Well, I'm gonna put this vertex at least in my application actually, and we're gonna make a new example here called triangle. For our engine, essentially. So Rust file triangle.rs. Triangle.rs, and we're gonna copy some code from clear color rs here. Right, but this time we wouldn't like go crazy with the windows and so on. Let's see. I mean, we're gonna remove this phase from ID. We don't need it, or actually we may need it to make some more interesting stuff. What else? I'm gonna simplify this a bit, possibly. Let's see. No need for this weird thing, like all the windows. Let's just say all the windows would have the same color. Let's say 0.1, 0.1, maybe 0.1, or like 0101, since this is sRGB. Nothing crazy. For now, we're not gonna have any add children here to keep things very simple. I'm gonna say 3, and in fact, we don't even need a primary window really. Let's just make a few windows, and that's pretty much it. Let's remove the primary window, just to keep things very simple. And what's next? Here we got the window event. All right, that's good. We're gonna keep it as it is. We're gonna remove this weird clear color stuff for now. We're gonna keep the elapsed though, if we want to do any animations for whichever reason. And yeah, and you're gonna have, so this is a basic skeleton for our new triangle example. All right, so let's run this. It's gonna be basically just, oh, what the heck? Well, hold on, let me change the example here. Dash example, triangle. Okay. So basically, as we go, we're gonna develop these examples right here in the engine. And so right now, I just have these 3 windows. Honestly, I'm just gonna make it 3. No need for all this ceremony. Let's make it 2 windows. Oh, fine. All right, so honestly, let's go with 0 0.1, 0 0.1, 0 0.1. All right, so we're gonna start here and we're gonna see how that goes. Okay, cool. All right, so let's see. So as I said, first of all, let's actually get this vertex struct. I'm gonna explain what's going on here. And let's put it in our application. Buffer contents, or you know what, maybe for now we could keep this in the render instead, just to keep things simple for now. Honestly, yeah, sure. Let's just go put it in the engine. Later on we may actually put it in. Hey, what is your OS? Nice DE. I'm using a Cache OS, which is based on Arch Linux, and I'm using KDE flavor. Right, so buffer contents import in vertex import. And this is like my vertex. All right, so let me explain what's going on here. So essentially in Volcano, we have these cool macros, derived macros, that helps us to describe the vertex format to the API. So we don't have to like write it manually in structs, like we're filling some you know, contract or something. Like here, for example, the position, you just tell it which it is. You just tell it that this is the format R32 G32 S float, which means that we got 32 bits for red and green, and type signed or like S float essentially, right? And we got here basically just a little array, F32 2. Though later on we're gonna use glam. Another thing we have is repc to make sure, because like the thing is about the Rust compiler is that it could you know, reorder fields and such to basically optimize stuff, but using repc would make sure that the ABI stays the same, so we could actually pass it to the GPU safely, right? And it would be valid, right? So repc, that's the first one. The second derive here, kind of like another macro, is buffer contents. And buffer contents just make sure that honestly, so basically you use this to be able to use it this generic in like buffers as a type, the GPU buffers as a type. Next up is the vertex trait. The vertex trait basically defines some, as you can see here, this is the macro expansion. It defines some functions for us that basically describe the layout of this vertex, so we don't have to write it. Otherwise, we would have had to rewrite this whole thing ourselves. But here, like Rust just kind of cleanly generates it for us. So that's our vertex struct. Next up is the window size dependent setup. Yeah, let's copy this and let's put it here. So what's going on here? Well, actually, we should probably put, yeah, we should put this into the swap chain target right here. So this is where the swap chain crap goes in. So where we're gonna actually do this, we're basically gonna go ahead and say here swap chain image views, essentially image views. Because before, since we were just using like the transfer commands, we didn't need these image views. But since right now we're gonna be using shaders and so on, we need those image views. And so like images are kind of like just, you know, memory blobs in some sense. They don't have any particular format generally, but the image views basically kind of like points to some image, right, like this one, but you could like change the format and so on, like which part you're seeing of the image, etc, etc. All right, so here we got the swap chain image views. Great. Now let's see what we got here. Let's swap chain image views. So here we basically go through every swap chain image and we map it to a new image view. Here basically Volcano helps us to easily do that using new default, and you just give it the image you're talking about and it would create a default image view for you. Right, without you having to fill another crazy struct like the row binding. And here we just add the missing fields. And why this is, all right, that's good. All right, that's great. And so basically we go through all swap chain images and then we collect it into a vector. And that's essentially what we're doing. Next up is, let's see. So after we acquire an image, currently in the acquired thing here, we're only passing in the pub create image. Now let's also pass in the image view. Right, there we go. The image view, and now what we're gonna do here, we're gonna basically add the missing fields, which is our image view here. And so we're just gonna basically index the swap chain image views too with the image index like we did here. Next up, in the present function, nothing would change really here. And yeah, that's basically it. The other thing though we should make sure is in the recreate swap chain, we gotta make sure to recreate the images, right? So self.swapchain image views, we're gonna recreate them here. And that's basically it. The other ones would, since they're gonna get overridden, they would automatically get destroyed since this is Volcano. So that's pretty much it for the swap chain target. Now let's go to the next thing, which is the render. All right. So now instead of using this clear color image function, which is a transfer command, we're gonna use something else. We're gonna use begin rendering. Now begin rendering takes a rendering info. So here we're using the dynamic rendering. So otherwise we would have to like basically create a render path first, then create a bunch of frame buffers for every swap chain image and all sorts of crap, which would have been crazy. But believe it or not, that's what the tutorials, most tutorials are using. Anyways, so here rendering info, and what we're gonna need. We're gonna need here color attachments. Alright, so let's actually open this up like a struct. And then we're gonna give it the color attachments. Wait, what the heck is going on here? Alright, there we go. So expected option Volcano. Alright, so this should be some image. Well, probably image view though. Wait, so the color attachment is basically vector of option. Actually, render attachment info, okay. And then here you give it the image view, which is our image view, but we didn't actually take that just yet. Let's actually take it. Image view, arc image view. Let's import it, and there we go. Now let's make sure that the render function does get the image view too. And how we're gonna do it, we're just gonna pass it from the Windows abstraction image view.clone. And there we go. Let's go back right now to the rendering code. Later on we may have some other color attachments, but for now we're good. Is there anything else that I need? Let's see the code here. So begin rendering, we pass in the color attachments, then we pass in the clear value, the store OP, and the load OP. Oh yeah, they're using that kind of thing. Interesting. So, wait, what? Ah, I see. So, basically what I should do here is take this and open up this struct and say dot dot, bruh. Wait. Right? Bruh. Kinda confused. What am I missing? We could add the missing fields here, and they have this field because we can't actually. I probably have something cursed here. What if we just like, let's try to just copy and see. So here, the Lloyd OP, so what we're gonna do when we get the attachment for the first time, we're just gonna clear it with a color, and store OP, we're gonna store the output result. Because sometimes you don't want to store the output result because you just like use it in some pass and like you just discard it afterwards. And here what we got, so self dot, well actually no, image views. Yeah. Here we actually pass in the image view. I'm not sure what was wrong with my... That's so strange. Either way. And we got a clear value here, which we pass in from the render params, of course. So the render params have this clear color. Dot into. And there we go. And that's basically how we begin rendering. And of course, since we begun rendering, we have to end it. End rendering. And for end rendering, what you need to give it, nothing really. Now between begin rendering and end rendering, you could do some rendering commands like draw functions and so on. Currently we're not going to be using image apparently, so we could even remove it if we really want to. Like remove the image, the renderer doesn't need that, just the image view is fine. And in fact you could actually access the image from the image view itself, which is also cool. So yeah, what we have here, oh yeah, I guess maybe it has some weird thing with the imports, maybe that was why the problem. That's strange. Either way, so let's see right now if this actually works. It should kind of be the same, but like with graphics clearing the screen. Oh yeah, we actually gotta set some things like the viewport and so on. But let's see what we got here. So image usage does not contain one of, oh yeah, I forgot about this. So when we created the swap chain images, or the swap chain, in the swap chain target here, since we were using transfer commands, now we're actually using render commands. Let's go with color attachment, and that's pretty much done with that. Now let's see what else it's gonna tell us. So these like the actual volcano validation, and there we go. Right now we're actually clearing the screen with with a graphics command, not a transfer command like we were doing in clear color. And that's basically it. Now next up, we need to basically draw something, and to draw something, of course, we're gonna need some shaders. All right, so we're gonna copy the shaders here. I'm gonna explain them. In fact, let's also copy the pipeline stuff too, why not? And the viewport. So this whole business right here up to here. Right, let's see. So where I'm gonna put this? Good question. Good question. For now, to keep things simple, I believe I'm gonna put them in the new function. So later on, we're gonna see where we're gonna put them. Right. Where is it? Hold on. Let me see. I mean, let's see what we have here. So volcano shaders. Oh yeah, let's actually make sure to add this volcano shaders dependency in cargo. This is the one that basically have these kind of macros to compile shaders inline, like this. All right, it's basically building. All right, so while it's building, let me see what we have here. So we got VS, a module called VS, and here we're using the shader macro. Here we give it a type which is vertex. Then here we got the version of GLSL, and here we're taking one attribute which is position, as you can see here, just like here, right, of location 0, of type Vic2, which matches this format right here. Okay, here we set GL position to Vic4, we give it the position, and the Z axis for now, since we have just a 2D position, we just say 0, hard code it to 0. And the next thing is module FS, which is like the fragment shader. And here fragment, type fragment, and layout location 0, output Vic4 F color. Mucho, you can use stds include str macro for embedding a file into your code at compile time. It is the same as writing out in literal, but you can store it in different file, lots of it. Yeah, I understand what you're talking about, but here we're using a macro, basically. We're using shader macro, which basically compile this inline. And if we had some error here, it would actually tell us the actual GLSL error in our Rust code. That's how powerful is like Rust macros. So as you can see, compilation error, shader GLSL 8, error, syntax error, and expected right brace, expecting comma or semicolon. If I fix this again, now it's going to compile. So it basically compiles at build time and it puts the binary here. It's used probably shader C under the hood. Oh, volcano is cool. Oh yeah, so cool. It like really does a lot for you, as you're gonna see in a second. Let's see. So, here we have an output, and we basically set it. Right now, we're just like hard coding it to the red color. That's the fragment shader. So the vertex shader basically goes through this main function here. Goes through every single vertex in the shader. Sorry, in the geometry. So of course every geometry basically is in games is made of triangles. It's all triangles. You've been living a lie. Right? And we could use this vertex shader to basically like transform the positions that we got of the geometry. And that's basically it. By the way, why shader C it is the best? I only keep hearing about GLSLC. Yeah, there's like GLSLC and there is another one. I believe kind of like the official reference thing, GLSL Lang. Yeah, GLSL Lang. So there's this one, and there's GLSLC. So GLSLC is made by Google, and it's basically using, I believe, this one, or maybe doing their own thing, probably. But either way, this one is very clunky to use. I actually tried to use it when I was making my C++ engine. And it was very weird to use, and there's no documentation that I can find about it. Right? But it was just a lot to just compile a single shader. There was a lot of crap that you have to do, you know, that you have to call and crap like that. right? So it was very weird, and that's the first thing. The second thing is that it doesn't support some like advanced features, like for example includes and so on. But Shader C is made by Google, right? And they basically support all of those, and it's very easy to use it to compile. In fact, there is a Shader C Rust library too. Rust. And we could use it later on to show you how we... In fact, here we go. This is as simple as it gets. You create a new compiler. You know, you specify the compile options. Like here you could basically set, for example, the optimization level, etc. And then here you set the macro definitions. In this case, EP, some main. So kind of like just CMake, right? You just define some macro here called EP, and this is its value. Then here you get the binary result. You just say compiler, compile into SPIR-V. And here you give it the type, in this case a vertex shader, and you give it the source code and the name of the file just for login purposes, and some options, and the entry point, which is main. Then you got like the binary that you could basically feed into a shader module in Volcano and so on. And that's basically it. Actually, wait. Binary results, yeah, and here we got the text result. Compile into SPIR-V assembly if you just want the assembly instead of the actual binary. And yeah, that's pretty much how you do it. You compile shaders at runtime using this. Though right now, since we're using the Volcano, like it basically does a lot for us already. At build time even. So two stones, well, two birds, one stone, right? Either way, let me try to explain the others. So let's see. What's the original repo for C++? Shadab Karim, welcome to the live stream. The original repo actually does work in debug, but it had a seg fault in release. But you could check it out. It's called Coda Chaco Engine without the RS. Let's see. Okay. Here it is. Nothing fancy, but it is using some like modern extensions of Vulkan, and it's using like Vulkan HPP RAI with wait, no, not this one. What the heck? Wait, no, not that one. Sorry, that was an old one, I guess, right? I think so, yeah, that was an old one. Here we go. Let me actually delete this one. Here it is. So created in a live stream. So let's see. Most of the code I believe was in, but it's not as good like architecture as this one though in Rust. So here you got the engine SRC, and you got like the most of the code was in GPU CPP. It was like this kind of like, you know, a monster struct essentially that is doing everything in C++. Look at that monstrosity, right? So this is the syntax that I was working with to use like the modern features of C++. Now look at this and look at, well, what is it? GPU, I guess. Wait, I believe driver actually, yeah, driver. So this is kind of a similar code. I mean, the Rust code is doing a bit more though, but look at that and look at this. So yeah, it's kind of similar there. But the syntax is like crazy, man. The syntax is very strange. Either way, you could check it out pretty much. Let's go back to what we had. Alright, so render CPP. So here we got the self keyword cannot be used. Self.device. So we had render. So here we basically have to say self.gpu. We sort that there, right? Oh, we actually don't have like self yet. Let's actually maybe put this code. this is the thing about abstractions, like kind of how I'm gonna do this. Let's see. Well, we already have the GPU here, my bad. GPU.device. Why did you choose Rust over C++? Message retracted. Method device not found in the current scope for struct GPU. Why? Oh yeah, we have the queue, my bad. So the thing is, to access the device, we have to go through the queue. Since I'm not storing the device, I could just take it from the queue. So gpu.queue.device, right? gpu.queue, device. Alright, next up. So what we have here, so we're using this macro to compile these shaders into a module, into a Rust module, and then these Rust modules would have a Lloyd function, right? We call this Lloyd function and would give us back an entry point, right? A shader. So Lloyd the shader as a shader module instead of doing the hard work ourselves. So here you just pass it the device, and then you tell it which entry point you're talking about, which is main in this case. The same thing with the fragment shader. Next up, we automatically generate the vertex. So like Volcano would generate the vertex input state for us. Otherwise, you had to do it yourself. Let me see if I could figure out how to like... not really, I can't. But either way, so it basically gets generated from the shader. It does a reflection for us. To actually do this in C++, you gotta do some weird crap. But either way, make a list of the shader stages. So here we just take those as shader stages. Next up, we got a pipeline layout, import. And here we just use gpu.queue.device. And let's actually just copy it. Well, and here we create a pipeline descriptor set layout. You need more subscribers doing these cool projects and not just web dev. Yeah, thank you so much. GPU queue device clone in wrap. Alright, so into pipeline layout, create info. So we're creating a pipeline layout from these stages. Right, into pipeline layout, create info. Honestly, you don't have to worry about these. They're just like, you know, boilerplate code. But essentially, at least in raw Vulkan, what you do is like you create this pipeline layout and you have to specify like the vertex input, the vertex format essentially. But either way, here we got one subpass. Let's import this, remove this, and let's see what we got here. The swap chain image format. Alright, so the swap chain image format. Well, we don't have it here, which is going to be interesting. But let's just take the image format from here. And whoever is using this code would need to figure out how to link this up, which is of course me, but just in another dimension. Right, so let's say image format. And what we got here. Expected volcano format, found image. Ah, yes. This should be format, not image format. Okay. And what next? So graphics pipeline, let's import that. And here, let's take the queue. GPU.queue.device, and let's call that because it's a getter function. And we're good. Let's import this. Alright, so here we just pass in the stages. Next up, we pass in the vertex input state, the input assembly state. Oh my god, this is wild. The viewport state, the rasterization state. The multi-samples. Don't worry, you don't have to like figure out all this stuff. This is just boilerplate code. But later on, like for example, when we want to implement MSAA, we need to understand what is a multi-sample state instead of just returning defaults. But yeah, so here we got the color blend state. This one is like how you blend stuff. Let's see, color blend state, like basically like when you're drawing multiple triangles on top of each other, how do you want them to blend? But either way, so here we take the swap chain color attachment formats dot length. All right, whatever, as long as it works. Dynamic state, and here we make the viewport dynamic state, so we don't have to recreate this whole pipeline, which is very costly every time the viewports get like the swap chain gets resized or the window gets resized. Subpass, some subpass into blah blah blah, whatever. Okay, import. And here the window size, we don't care about windows here. This is just a render, so we're just gonna take some extent, essentially. So what type of extent that is? Oh yeah, just F32, okay. So let's take that from whoever's calling this. So extent F32 2. Okay. Viewport. Well, we gotta also include it here. Why not? In fact, we need to include all of these things. So we need to store the pipeline here. We need to store the viewport. And what else? And these are just like modules. These modules, actually, you could put them out of here. You could put them, let's say, here with the vertex stuff and so on. And yeah, so here we're just creating the pipeline. And notice one thing is that this is inside of a block. So these shader modules, after we created the graphics pipeline, these would get destroyed, right? So because we're gonna exit this scope, right? Because we don't need them. After you're done with the shader modules, after you made the graphics pipeline, you don't need those anymore. So you could destroy them. So now let's just store this pipeline and that in the renderer here. We may move this pipeline out of the renderer. I'm not sure. We'll see about that. I'm not sure how I want to structure this just yet. Only the code would tell me how I'm going to do it. Reed, welcome to the live stream. How has writing your engine in Rust been? Any pain points so far? It has been a very nice experience, other than the raw binding of Vulkan was kind of raw, right? And like it was unsafe everywhere, and it wasn't like exploiting the whole Rust tooling, you know. But I basically just refactored to Volcano right now, which is like a safe Rust wrapper around the Vulkan binding. And it's been very nice so far, like very, very nice. One thing, for example, here I could show you is that, for example, the vertex shader and like the shaders are getting compiled for me using just macros. Like literally a Rust macro is compiling shader, you know, at build time. And basically showing me the freaking error of the shader inline. That's how powerful are, like, for example, macros here. That is crazy. And it's embedding all these bytes inside of here. Notice that. That is crazy. That's first thing. And it's even giving me reflection. It's doing reflection at build time. And it's giving it to me here. So I could use it without me having to specify every single vertex format. You just like define this, use these basically these macros, and it just works. And these macros are very clean, like they're derived macros. They're, you know, using the actual language tokens, not just, you know, define this and define that like in Rust, in C and C++. Either way, let's go to the next thing. What we had here before. So here we're storing the pipeline, and finally we store the viewport. There we go. And next up, what we're gonna do here, let's add these fields, and now we could actually use them here. So after begin rendering, we can bind that pipeline. Bind pipeline graphics, and here we give it the the pipeline that we're talking about, which is here our pipeline. And is that it? We should probably clone this arc. And next up, what we need to do, well, we're gonna need some actual buffers, some vertex buffers. So let's go back to the example here. I'm gonna copy the code again, and I'm just gonna explain it to you. Where is it? Because I'm not very familiar with the API of Volcano. I usually use only the row binding. So let's see. Memory allocator. That's great. I have been doing something similar. I was writing an image viewer using Vulkan and C. I'm restarting in Rust now. The fact that there are high quality Rust crates have been the best. Yeah, the ecosystem. Oh my god. So I'm probably in this live stream things like the next live streams. I'm probably gonna try. I never done this before, but I'm gonna try to make hopefully a UI library, right? Our own UI library. And the thing is, I found a lot of libraries I can depend on. For example, for the layouts, I could use the library Taffy Rust. This is a high performance Rust powered UI layout library. So I don't have to roll that on my own, right? It would give me some powerful layouts itself. It's kind of like CSS to some degree. So I get that for free, and it's pretty good. Like, I could easily add this library and so on. That's one. The other is Cosmic Text for text rendering. Not rendering, but like, let me show you. Cosmic Text. So this would do some handling of the text, like even Arabic, as you can see here, and all sorts of cool text. So like text shaping, layout, render, etc. It would handle this for me, and I could use another library. What else? What is it called? I don't remember the name of the others that I found. But basically in Rust, like, you could find libraries for everything, you know. Just like, people really use libraries a lot because it's very good. In C++ though, everyone tends to roll his own thing, you know, from scratch for no reason, and it's usually way worse. But yeah. I don't remember the other ones that I wanted to use. Either way, we're gonna see later on. All right, so what's next here? Oh yeah, we wanted the... let's remove these. And let's go back to the example here. All right, so let me just copy this code, which creates some buffers here. Oh well. Yes, same as C, I lean more, but my product is worse, it seems, unless I spend a lot of time. Not really. In C, also, it's even worse than C++, actually, because you don't even have a great standard library. Like, you don't even have a vector, you know. Though, what I like about C, at least, is that things are very simple. Like, there's no crazy weird crap going on behind your back. Right, it's very clear what's going on. Like, here you're allocating memory, here you're getting the reference to a memory. There's no weird things like move constructors and so on. But either way. So let's get this. But the thing is, we're gonna need the command buffer allocator and these weird things. Well, I guess we'll figure it out later on. We'll see. All right, let's take this and put it before even maybe the pipeline. Why not? Let's put this here and see what we're gonna need. So here this would need like a memory allocator and so on. So we can actually delegate this to the GPU class, really, which would help us to create this. Yep. Let's go ahead and do that. So let's go to the GPU class. And let's go down here and let's say create, I guess, buffer or something. We'll see about that. Either way, we're gonna copy this code and let's see. So we don't need inwrap, and let's import these volcano buffer. And here we're gonna use the stored memory allocator that I created before, and of course I need self here. And I don't want to add semicolon, just return whatever type it's returning, which is this, right? So it just generates that for me, which is great. That's strange. Either way, we'll see. I guess basically here we need a generic, and this is how we do it in Rust. So as you can see in Volcano, you actually have the buffers generic on the data type. Like in this case, it would probably be the vertex, right? But either way, buffer from iterator. Here you give it the memory allocator that we created at the start for the GPU, right, for the device. Next up here, we got the buffer create info. Let's import that. Buffer usage, let's import that. Allocation create info, let's import that. And we're gonna decide what we're gonna like. And here, basically, this is the data, right? And let's see what we got here. So let's start by the data. So we're gonna take the data from the user, and we're just gonna basically mirror the syntax that we have here actually. And what is it? Wait. Let's see. So we're getting an iterator I. Iterator I, and I is, whoops, where's I? Oh, here we go. I just remembered like Rust generics. I is basically into iterator item equal t into iter. So here's what I'm gonna do actually. So I'm gonna grab this generics, I'm gonna steal them from here and put them here shamelessly. Right? That's the first thing. And data would be an iterator I. Next, we're gonna steal these two. Right? Where this, like, and just do this, and there you go, boom. All right, that's sick. Clone the allocator, and there we go. Done. Next up, let's see what we're gonna give to the user next. So of course we want the user to be able to change the usage here to the buffer usage he needs. The user, by the way, is me. Anyways, that's the usage. Next up here we got prefer device and host sequential write. So actually this is like really a staging buffer. So here you basically tell it where you want this buffer to be allocated in. Here in this case we're telling it to prefer the device, to prefer the VRAM, right? But we want it to be host sequential write, so we could actually write to it from the host sequentially. You don't really have to think too much about this, honestly. But yeah, this is, we could even call it like staging buffer, or honestly it's just call it create buffer really for now. Fine. And that's basically it. Now let's go back into our business, into our renderer, and now we could actually create a vertex buffer sanely. Vertex buffer is equal to gpu.create buffer, but I forgot as always to make this public. Of course, only maybe in the current crate. Right, and then here we could say create buffer. There we go, and you pass it your iterator, which is in this case vertices, and then just inwrap the result, and of course it should be right now an anyhow result. And let's see what we got here now. Okay, so we also need the buffer usage. So what we're gonna use this buffer for, of course, to store vertex data. So we tell the driver that we're gonna store vertex buffers, vertices here, so we could optimize for it. And the nice thing about Volcano is that this is actually typed with our vertex struct, as you can see here, which is cool. So now let's see what we're gonna need next. And yeah, that's basically how you create a vertex buffer. It's really that simple. All right. Now that's great. And this of course is our vertices data. Yeah, also there's another crate that we could use to create, like, to generate these vertices for our UI library, which is called Leon, I think. Leon, if I remember. Leon Geom Rust, I believe. Yeah, so this library, we could use it to tessellate geometry. What I mean by tessellate is that you basically describe to the library some shape. Like let's say you want a circle to render a circle, or you want to render a bounded rectangle, or sorry, not a rounded rectangle, or some shape like this, some Bezier curve or something. Now the thing is, you can't really tell the GPU to render this. No way. You can't just give it a Bezier curve that easy. I mean, if you're insane, you could probably create a shader for that, like a compute shader. Though even if you make a compute shader, you still have to tessellate. What I mean by tessellate is that you have to turn, like, let's say this parametric equation, like this Bezier curve, this mathematical expression, into geometry, which is basically just triangles, right? So that's what we call tessellation. You convert this perfect shape or vector into, you know, segments like this that you could actually push the GPU to render. So we could use this library to basically tessellate for us, so we don't have to figure out the math ourselves, right? We could tell it, for example, tessellate a circle of this and that radius and so on, and then it would give us the vertices that we could push to the you know, to the GPU to render, which would be cool. We're gonna try it later on, but for now we're just gonna stick to this little triangle here. Either way, now let's store this vertex buffer, please. How are we gonna do that? Well, let's say vertex buffer arc. Well, actually, what is the type of this? The type of this is subbuffer my vertex. Okay. My vertex like this, or what? Yeah, I think so. I believe. So now let's try this out. Let's add the missing fields. Good. And the other thing, we could make these into, we could replace them with that. Same thing with this. Since we're turning a result anyways. Expected anyhow, yeah. Since we're returning a result now, I should say okay here. And there we go. Mismatched closing delimiter. Okay, good. Now we're great. No method named found for... Oh yeah, so let's actually unwrap this result. So now that we bound the pipeline graphics, we need to also set the viewport though. Well, in fact, let's set it first maybe. I don't know. Let's set the viewport. I don't think the order matters in this case. But the first viewport is 0, because you could have like multiple viewports essentially, but here we just have one. So expected viewport found viewport 1. What the heck? Let me see the example code real quick here. Like set viewport. Here we go. So it's basically saying into iter.collect. Okay. Into iter.collect. So we collect it into a vector essentially. It's a small vec, by the way, if you notice. If you notice here, it's a small vec. This is also something that like Volcano is using. It's not using vec, it's using small vec. What means small vec is that as long as this vector have only up to 4 elements, then it's going to be stored in the stack as an array. So we don't have to allocate anything. And we're using this since we know that at most, everybody would have like at most 4 viewports, right? Otherwise, if there is some weird user that have more than 4 viewports, then we're still gonna accept it, but we're gonna at that point we're gonna need an actual vector allocation, right? But the other users don't get penalized; they just use like an array, which is great. The other thing here is that what we need else. We bind pipeline graphics, then we bind the vertex buffers finally. So let's bind the vertex buffers. Bind the vertex buffers, and here what we need, the first binding, which is 0, and then finally the self vertex buffer. You could pass multiple vertex buffers there because it's an iterator, but other than that we're good now. I think maybe that's it, really. Is that it? Did I miss anything? I think I didn't. Let's see if this works. You know how much steps we have like skipped over because thanks to Volcano, like bruh. It's really doing a lot for us. Thank God. Alright, so it's compiling Volcano right now, I think. Alright, so we have some error here. Oh yeah, when we create the renderer, now we gotta figure out those those arguments we delegated before. So here we're basically creating in the application, we're creating a renderer. And we basically need to tell it which image format and extent. The image format and the extent. We need to get that from the swap chain, but the question is, our swap chain right now is in the Windows abstraction. So I guess what we're gonna do then, we're just gonna say maybe, and what we gonna need other than that, by the way, we're gonna need the image format and the extent. Alright, so let's figure out how we're gonna expose that to the application. So currently what we need is the swap chain targets. Alright, so let's see what we got. So we're gonna basically have another function here called get format, I guess, and then the ID. Then we basically grab the swap chain target, and then we grab the, well, of course it's not that simple. Let's see, so let's actually define this image format function. Fine. Wait, let's create a method image format inside of the swap chain target. Oh yeah, and here we can access the swap chain. All right. And here we're gonna basically return swap chain the image format. Right. And of course we don't actually need option here really. And let's go import. And the other thing that we need to expose is the extent. So pub create fn image extent. And there we go. Cool. Now let's go back to whoever is using this and let's see what we got here. We don't need option really. You could just take the format directly. Right, expected option but found. I see why they use the format. I see. So, because like you could have that the swap chain targets doesn't have that window ID. Expected option but found format. But why you're expecting? Actually, instead of doing and then here, let's say map. I guess expected format but found. Oh yeah, good. So what I did basically here is if we found a swap chain target with that particular ID, then yes, we're gonna map it into its own image format. Otherwise, we're just gonna return none. That's basically what this map does here. And that's, yeah. So like get image format, or we could just say image, call it image format really. Now let's see here what we got. So render new, and let's see, render, let's just take whatever, Windows dot get. We need some window ID here. How are we gonna get it? Good question. Let's cheat a bit. Let's take it from the clear colors real quick here. So let's say keys dot next, I guess. Dot in wrap. And then yeah, right. So this is like our window ID. What are your favorite games based on visuals, graphics, tech? I don't really care that much honestly about the graphics of the games, though I have, like, I like, basically, for example, let me just tell you the games that I like pretty much. Like, of course, Minecraft, that's for sure. And there's Factorio, there is RimWorld, there is, what else? There's also Europa, I think, Universalis. Yeah. What else? Euro Truck Simulator 2. You know, all those kind of like simulators, like Farming Simulator. What else again? Though, unfortunately, I don't really play games recently, especially since I, you know, kind of grew up. I don't really feel like every time I hop into a game, I feel like I'm wasting too much time. It's like I really want to enjoy the game, but I just can't anymore, unfortunately. And that's why I also steered away from game development, because I don't enjoy it anymore. Because like I started as a kid, you know, so at that point I was kind of enjoying it. Although I started anyways, just because I want to know how it works really, because I thought at that point I wanted to know, like, I wanted to create games, but maybe I didn't really want to create games. I just wanted to know how games are created. And that's how I finally dig into game engine development at the end. But yeah, because the thing is about games is that it's more than programming, and I don't care about the other parts of the game development process, like game design and like art and music and so on, and like storytelling, and there's just a lot of moving parts that goes into actually creating a good game, and especially a fun game. And the thing is, for me, a fun game is not like a regular game that people find fun. My kind of games are like very nerdy. Right? So also I like another game called, wait, what is it called? It's like an assembly kind of game. You have like a guy that you kind of program in like an assembly kind of language. What is it called? Truly don't remember the name. There's at least 7 billion human game. Yeah. There we are. So this is one of them. This is one of, because like this company that created the developer Tomorrow Corporation. Yeah, they have two games. They have this 7 billion humans, and they have another one. Let's see. Tomorrow Corporation. Have you seen their engine demo? Not really. What is engine demo? Yeah, this one. The Human Resource Machine. This is the first game that I've seen from this company. Oh my god, so much fun. So basically you have a little guy that you kind of like program in a little simplistic assembly language. It's pretty cool. And then they released another game called 7 Billion Humans. And it's very interesting because like here you had one guy, so, and you were kind of like programming that guy to pick boxes and like calculate stuff, and you have the floor as memory and shit. But here in 7 Billion Humans, you have like multiple humans, like you have multiple of these guys, and you have to program them at the same time. So it's like this is like CPU programming in assembly, and this is GPU programming assembly. So like this is, here you learn single-threaded programming, and here you kind of learn multi-threaded programming. Like you're programming multiple people at the same time in some sense. Right. Yeah, I love that game, 7 Billion Humans and Human Resource. Yeah, these two games are really like one of my... I would definitely like replay these games. This is like the only game that I can think about that I can replay. There is another one though called Tomorrow Corporation Tech Demo. I should really check that out. I never checked that out. But like these two games are really, oh my god. The other one was Turing Complete. There's also Test 100 though. Test 100 is too hard. I'm not that crazy. Though I did actually pass some a few things, and I mean it's also interesting, it's also great, but it's a bit too hard. Like at that point, just, you know, just like program assembly directly. right? But the nice thing about the 7 billion humans and human resources, you kind of forget completely about something called syntax or computer. You just have a little human, you drag blocks around, but it's still kind of like a simplistic. So the thing is, there's a very thin line between making a fun game and making like a hard game, right? So it's quite wild. Either way, there's another game called Turing Complete. This one is also very amazing. I really recommend it. So here you basically create your own computer from scratch, right? Using logic gates. So you start from an AND gate and you create your own computer. So you go puzzle by puzzle, right? And at the end of the day, you create your own assembly language, your own processor, your own CPU, your own memory, etc. So it's very lovely game. I really, really love this game too. It's so amazing. So much fun. You also create like, then after you create your own CPU and your own RAM and your own assembly language, then you basically create a game in it. So much fun. And yeah, these are the games that I really like, pretty much. There's Test 100, that's two. And yeah, there's also another one that is by the same developer that made Test 100. Test 100. Who made it? Zachtronics, yeah. Zachtronics, like all the games of this guy, pretty nice. Right, this one, Shenzhen IO. Like you kind of program microcontrollers in a little simplistic assembly language, and like you have multiple controllers and they have states and so on, power. There's Test 100, pretty much. They also have Infinite Effect. Yeah, these games are pretty cool. Yeah, that's that's it. All right, let's go back to what we were doing. I forgot completely what we were doing. To be honest, I really appreciate the geometric as what you said there. Geometric aspects of opus magnum. I didn't understand really the concept of opus magnum. I'm not sure, but yeah. Either way, what we had here, let's see. Oh yeah, so I was doing window ID is equal to this. Right, so we get a window ID, then we use it here to get some window. Actually, not a window, but like, wait, what the heck am I doing here? Wait, what? No, we want to get the swap chain format for image format. Yeah, I believe image format though. Maybe I didn't make it public though. Yeah, I probably haven't. So let's make this public. And we also need another function to make public, is the image extent. Yep. And that's basically it. Or honestly, you know what? I mean, yeah, we could make it, but never mind. Let's just go on. Let's continue. And here what we need to do, so basically let's just store honestly an image format here real quick. So we really need to kind of polish this up, this API. I'm just not sure yet how we're gonna do it, but for now this is what we got. So value moved here. Yeah, I see. So let's actually put that there and then render new. So here we could pass in the format, the image format, yeah. And then here the image extent. There we go. Oh, expected F32 2 but found U32. That's interesting, huh? Yeah, that returns U32. Oh yeah, but I guess the render is expecting a float, right? I think so. And let's see. The renderer extent, where the extent is being used. Here. Oh yeah, so the viewport is expecting like float. Alright, let's convert it. So we're just gonna create this and say image extent dot. So basically the first one, I guess, and as f32 and expected f32. What? Oh yeah, there we go. Perfect. So that's how we pass in the image format and the image extent. We should really polish this up later on, but for now this should be fine. This should be enough, I guess, to run this demo right now. And if everything went well, then we should get a triangle. And no, it didn't go. Let's see why. Let's see. Render new. Image format. And what's going on? So here we're redrawing. So let's see the renderer again. Am I missing something? So we're creating the graphics pipeline. Creating the vertex buffer out of the vertices. And so then what's the problem? Set viewport. Maybe we have to set the cursor, sorry, not the, wait, bind graphics pipeline, vertex buffer, and rendering. Let's see if I'm missing anything from here. Let's start by the commands. So we're setting the viewport and we bind in the graphics pipeline. Then we're binding the vertex buffer. Oh yeah, we need to draw. We haven't drawn anything yet. And then we end the rendering. And apparently the draw function is actually in safe for some reason. That's why they couldn't do it directly. I see. So that makes sense. We're not drawing anything yet. Builder in rendering. Why this is in save, by the way? Let me see. The general shader safety requirements apply. What? Interesting. Anyways, self vertex buffer length as U32. Come on. So here we can say length. You know why? Of the vertex buffer, because the vertex buffer is actually typed. Now usually in, let's say, you know, raw vulkan, what you would do actually is you would get the size in bytes of the vertex buffer, then you would divide by the size of the vertex. But since this is like typed by the vertex, then you could just say length, just like a regular vector. You're not working with bytes. Volcano does that for you. So that's pretty cool. Lovely. Now let's actually try this out, and we should get a triangle at this point. And the second you get a triangle, everything else becomes a little bit easier. Right? And here we go. But wait a second, why this looks this way? Oh yeah, we're not setting the viewport. Yeah, when we resize the window, we don't set the view. And you get this interesting thing, you know. Yeah, it's an interesting effect. This is what happens like when you resize the window, you don't resize the viewport. That's interesting. So let's make sure to resize that thing. How are we gonna do it? Is the extent the only thing why we're taking this? Yeah, apparently. Well, let's remove it then. Let's remove it from here. No need for it here. Okay. And we're gonna actually create the viewport here instead. Don't we have the size already? No? Let's viewport is equal to that. Viewport. Now what's going on here? Let's steal the viewport again. I should have copied before I removed it, but anyways. Alright, and here let's take the extent again here. Whoops. Extent. Well, actually, wait a second. Should we put it in the render params? Or no? Not really. Fine. Let's just keep it this way. And here we get set it to f32 2. Now when we actually render, we need to pass it that. I'm pretty sure maybe we have the extent here, no? Not really. Weird. But wait a second, how about... Wait. Can I get the size from here? Because sometimes Volcano does store like stuff like that. Like maybe create info or... Wait, let me see what we have here. Volcano sometimes store those stuff for convenience. Oh my god. We don't actually have to store a format. As you can see, we can just take it. Yeah, there you go. The extent. Here we go. So the good news, since we're using Volcano, we don't really even have to worry about this crap. That's one thing. Though we still need the image format. There's no way we could take that, right? Yeah, we still need the image format. Though we don't need the extent anymore, at least here, and we don't even need it here either. So that's amazing. So the extent, we could just take it from the image view dot extent, image dot extent. Though we need to convert it into that, I guess, or can we? We can't, because this is like an array of 3 and an array of 2. Because the thing is, images have like a size of 3 dimensions, because you could have like 3D images. For example, for volumetric data, those are like 3D images. Basically, 3D images basically means just like a lot of images stacked on top of each other. Or like, for example, maybe you're making Minecraft, then you're gonna have like a texture array, and that's essentially a 3D image, right? Because like you have an array of 2D images. It's basically a 3D image, right? And that's why we have that. But here the viewport is expecting a 2D extent, not 3D. So, well, I guess we just gotta do it ourselves, unless if Volcano have some other weird thing that we could use, but I don't think. Yeah, I don't know. Well, fine. Let's just take the extent here. Let extent is equal to this, and here we're gonna say extent.x, comma extent, well, actually not x 0, comma extent 1, though as f32, as f32. Oh my god, that's so cool. So we don't have right now to worry about where to get the extent here. So that's pretty sick. The other thing here is that we don't need extent anymore. Where is that thing? Yeah, in triangle actually. Where is it? So we don't need the extent here anymore. So that's good. And so we don't need this function either, nor this function. So let's remove them for now. But you may need them later for something else. I don't know. But for now, at least I don't. Alright. That's cool. And now we don't need this function. So we still have only one thing, which is the image format, which I don't think I could figure out some way here for now. But we may see later. Like for example, maybe we could let the user pick the format himself, and then he could reuse it here. So you can make sure also that all the windows use the same format. But we'll see about that later on. Either way. Also, we don't need I here apparently. And yeah. Anything else? I don't think. Right now, we should be good. Let's see now if we okay, so if we resize this right now, as you can see, and the resizing, oh my god, so freaking smooth because of WinIt. Look at that. Alright, cool. So now we could try some, I guess, animation maybe. And how are we gonna do it? Well, good question. So now we have a triangle. What we should do next? Good question. Well, first of all, let me change that freaking color to at least something. I mean, this is triangle sample, yeah, so we're done. Pretty much done. Though, let's see the other examples. Is there something else that we can check out or try out? I don't think. Right, so I'm gonna grab some water and gonna come back. Okay, back. Well, all right, let's see. So the thing is right now we're actually having all that drawing code in the actual engine, which is not what we want, at least for the vertices, for example. So, because right now the clear color, first of all, we need to fix the clear color example 2 now. And how we're gonna do that? Well, we're gonna take the image format here. And you're gonna put it here. Well, wait. Yeah, like that, I guess, and need the window ID too. Oh my god. What's going on here? Oh yeah, so this self.windows should be here. There we go. Now the clear color would also show the triangle, which is not what we want. So let's see how we could decouple that. Alright, so let's go back to the render now that we have tried this out. So how are we gonna do this? So honestly, the shader should be in the application code. Alright, and then basically the vertex buffer should really just be passed into the render function. Right. Yeah. Now this is gonna make it a little bit, well, actually, all right, let's try. So we're gonna take this guy here and gonna put it in the actual application code. So let's import this stuff. And what else? So now we got that out of the way, cool. Now here in the renderer, well, we also gotta take this vertex buffer and remove it from here. And we don't need to store a vertex buffer here, only the graphics pipeline really. And what do you think about WGPRS? Chad, welcome to the live stream. WGPU is also good. WGPU is also great. It just depends on your own, like, what is it called? Your own priorities, really. But like both Volcano and WGPU, both are some APIs that I would really recommend. So yeah, that's my answer there. Let's see, triangle. Should I bury myself? Why? Let's see what we got here. Wait, I'm so confused right now. Where we were? Bruh. Oh, okay. I see. So where should I store this? Oh yeah, in the application, my bad. Right, so let's actually store a vertex buffer here. But honestly, for that, we're gonna make a mesh really instead. Yeah, let's make a mesh. No girlfriend, no job, no degree, no life. I mean, you're not alone. There's just a lot of people like that nowadays, unfortunately. Alright, so let's make a mesh. How are we gonna make a mesh? Struct. Whoops. So where are we gonna put this? Should we put it here or? I guess fine, yeah. Let's put it here, and it's gonna be public. And I see. So this is where we're gonna put the. What is zoomer? I do remember that term. Struct mesh. Alright, so how are we gonna store this? Well, first of all, let's put this Gen Z member. Oh, well, depends on what is Gen Z. I know what is Gen Z, but like what it is exactly, I have never researched about that. Alright. Let's see. There's just too much going on here. Let's remove the stuff that we don't need here, so I don't get distracted. Like born in 2000s. Yeah, I am. Alright. Let's import this. And so here, yeah, okay. So how are we gonna do this? So we're gonna put vertices here, but the buffers would be created in the renderer. That's basically how we're gonna do it. We are the transition between old cool OpenGL 1.1 shitty stuff and Vulkan. Yeah, it is. It's like in a weird place. Essentially, like you either go burn yourself with Vulkan or go burn yourself with OpenGL. One of them. Both suck. So let's see. I would still go with Vulkan, honestly. I'm not sure. Hopefully I wouldn't regret saying this. We'll see. All right. Let's vertex buffer. Yeah, we're gonna make basically implementation for mesh here. FN new, because I always tend to regret things that I say. Especially when it comes to technology, like things really change really quickly. I don't know. It's like the thing is, I don't really care. Like when I find that something isn't working, I just change my mind directly. I don't really stick to things that I think don't work anymore. And that's why you find me like trying various technologies pretty much. Let's see. So if I think like C++ is the best, then I'm gonna go with C++. If I think Rust is the best, then you'll find me going with the Rust, right? But yeah, either way. So here we're gonna need subbuffer actually. Subbuffer vertex. Though I think I'm gonna be sticking to Rust for a very long time. Though, who knows? Honestly, at this point, I don't like to say anything anymore. Are you Eastern European? No. Let's see what we got here. So this should actually have... Well, honestly, should we like make the vertex generic? Are you from Asia? No. What do you think? Would it, like, guess, not just like ask me all the countries in the world. Well, all the what is it called? I start to forget a lot of things. No, I'm not from South America. Like, guess one. You still have only one guess left. Let's see. So here we basically gonna take low IQ for that. Vertex buffer vertices. Let's turn on Sherlock Holmes mode. Right. So I mean, let's try. Let's see what's gonna happen if we take a generic vertex here. Based on our time, it is 3-5. Good. Implement vertex. Then here we're gonna basically take in vertices of let's just take, honestly, span. Let's keep it very simple really there. And then, well, we're gonna need a GPU. Huh. Must be from Portugal. No, I'm not. I had one guess, unfortunately. Let's see. Trait bound is not satisfied. Like, what do I like? What's my accent? Seems like. What kind of accent I have? First of all, where are you from? Ana Cote d'Ivoire, Burkina. No way. No way. Vertex buffer. Subbuffer vertex. That's strange. What the heck? Create buffer. Why this is a reference? Interesting. Can we say maybe into iter? No. Well, I guess maybe we have to like do this weird thing again. Oh my god. Let's try it. So how are we gonna do this? Like like this or what? Or you know what? Let's not overcomplicate things. Can we say Vic Vertex instead? Yeah, that would work. Although kind of suck, but it works. Okay, and then what? Consider restriction type parameter vertex with trait pod. Sure. So it needs to be restricted by bytemap pod. So we're gonna add that to dependencies. MD, check the first second of this live stream and you'll find out. Oh yeah. Create buffer. Consider restricting this type parameter. So we need all these traits apparently. Okay. But like seriously, like what my accent seems like for you. Especially if you're natives. Are you natives? Like speaking English natively? If so, what do you think my accent seems like? I don't know. I have no clue. Vertex buffer. Alright, so I've been juggling some generics apparently here. So vertex should be bytemap pod, send and sync. Alrighty, and then we could create a buffer of type vertex buffer. And then here, this needs to be a result. Anyhow, result self. There we go. And what's going on here? Well, this should be okay. Okay, whoops, let's go. And what else? Use of an undeclared creator module vs. Yes, so this one we're actually gonna take it from the user. But wait, do we even need to store the pipeline though? I mean, we need to create, yeah. But so what we're gonna do here, we're gonna say, I guess, maybe vs entry point, I believe. Yeah, probably that's what I'm gonna do here, I guess. Entry point. And then the user is supposed to actually do that. But then we have to freaking use the vertex here again, apparently. That's interesting, huh? Oh, whoops, no. What is this? Oh, it's a trait that's imported somewhere here. That could have easily tripped me out. So let's say as vertex trait. And used import. Or just remove it, yeah, since we're not using it. Now here what we got, so vertex. Vertex needs to be basically well, a generic. And it needs to be bound by the vertex trait. So the thing is, of course, I can't. So I gotta say vertex trait here, and then I could use that here. You're from Morocco. Yep, Morocco. Exactly. Do my accent seems Moroccan? Vertex per vertex definition. VS FS. Alright. We got the vertex buffer, the pipeline. So the render would only contain, for now at least, the pipeline and the GPU. Now, let's go to wherever we're creating the render here. Your accent looks like Middle Eastern, in fact, but I would not guess, really. I see. Are you native? Like, are you an American or? Let's see. Make Q public. Well, good question. Well, fine. I mean, we don't have another option right now. So we're gonna have some very rough edges, because right now we're not like, the problem that we have here is not, we're depending on volcanoes like macros and such, so we can't really do much in terms of this part for now. So we're just gonna have to play around it, apparently. Right. VSFS. MD has to be Macedonian. Let's see. Cannot use the operator. Sure. Let's say in wrap. In wrap. Cool. But now we actually gotta create a mesh out of these vertices. So mesh is equal to mesh. Wait, mesh new, right? I guess maybe it's not public, right? Let's see. Yep, let's make it public. And so the mesh right now requires the GPU, which we have, and the vertices. Now let's take this weird thing here and let's put it here. And let's make this clone. And here vertices. Huh. So expected vector of found my vertex 3. Interesting. I mean, we could just collect it into a vector for now. That's not the best way to go about it, but fine. And then let's unwrap this. So now we got a little mesh. Now we gotta store that. And also, as you can see here, it became a spaghetti of options. We really should make a little struct here to help us with that part. So this should be option mesh. Right. And missing type argument. Well, the missing type is basically vertex, but we gotta make sure that this is as vertex straight. Otherwise it would clash. Now, vertex, we could call that vertex into the my vertex. And here we're just gonna call this vertex straight. And yeah. Whoops. We could call this vertex 2. And there we go. Perfect. Variable mesh is never used. Yep. Well, this, by the way, should be into iter, really. Yeah, and then we're gonna say self.mesh is equal to mesh. Now, well, we're gonna say some mesh, yeah. Okay, that's cool. Now what? Yeah, we gotta basically need to pass that to the render function now as a render parameter. But where is the redraw requested? Here we're gonna give it a mesh. Now mesh by default would be, well, we're just gonna honestly give it self.mesh, and in render params we're gonna have a public mesh, I guess. option mesh. Oh my god, we're making this too generic. Should we just stick to one vertex format? Well, let's just go ahead and do this. All right. That's basically it. Okay, and then what? So now if we have a mesh, we could add it here. So if let's sum mesh, something I like doing is instead of having type as a generic trait, some trait, I have an associated type trait. Type T makes stuff much easier. Does it apply to something I'm doing here? I think maybe I know what you're talking about, but at the same time I don't. So I know what is an associated type, but I'm not sure if you've seen some way to apply it here. So how are we gonna do this? Well, render params, yeah, not mesh. What we're gonna do here is select self. Builder dodge bind vertex buffers. Self dot. Well, here we're gonna say mesh dot vertex buffer, and there you go. But yeah, we're gonna also need this now. So whoops, let's go. You're basically gonna say, now imagine doing all this stuff using role binding. Oh my god, I don't know what I was thinking. For example, we want to store multiple meshes with different vertex layouts in one collection. But like, does it apply to something I'm doing right now? Well, we need the length. Let's store the length. So mesh vertex buffer dot len, and here, well, this is basically the vertex count though. And then we could use it here as u32. And that's basically it. So if you have some mesh, then we're gonna use it. Now, cannot move. So what we're gonna do then? Should we just clone it? Or what should we do? Well, good question. I think subbuffer is clonable. Maybe. I mean, let's try to derive clone. I think it's like, you know, yeah, it's probably like, wait. I'm not sure, but I think it's probably like an arc or something like that. So it's cheap to clone. I could be wrong though, but for now, yeah, I think so. I mean, the subbuffer, after all, is just like a view. It's like a span or a slice in Rust, I believe, if I understand this right. Because the actual own thing is called buffer, not subbuffer. And that's the thing. Yeah, pretty much. Now, how we're gonna do this is we're gonna say, where the heck is that? Okay, here. Self mesh clone. Why the heck do I need iter? Bruh. Why can't I just say clone? That's weird. I don't know what happened there. Either way. Wrong number of type arguments expected. What? Oh yeah. Here apparently we need vertex. And there we go. How about now? The trade bound vertex by mark pod is not satisfied. What? For vertex. So where this is in mesh new. It said basically that the vertex, I mean, it's buffer constants though. Oh, I think maybe I know what's going on here. Hold on. If we go to here, instead of byte mark and all this crap, we're just gonna say buffer constants really. Import. And I think that would do the same exact thing here. Yeah, there we go. Alright, so we don't need byte mark there. Now should we actually just like fixate the vertex to the render? I don't know. Either way, this is working, I believe. Let's see now. Well, the mesh is an option. I guess as ref. Wait, what the heck? Weird. Oh, maybe vertex should be cloned too, maybe that's why? Probably. There we go. Perfect. So now our abstraction is actually generic on the vertex, which is cool. And honestly, we could remove this for now. And that's how you make a triangle using the engine. Pretty much. Let's make sure that we didn't, yeah, we definitely have some problems right now with the clear color example. Oh boy, we need the shaders. But right now we don't have any shaders though. Triangle milestone reached, yep. Should we just remove the clear color example and call it a day? Yeah, honestly, I think for now, I'm not gonna really maintain, I guess, multiple examples because it's just too much. Like every time you change something, you gotta basically fixate or fix like multiple examples at once, which is gonna suck. I mean, it's good to like, what do you guys think? Should we just keep one example for now, or should we just fix this? Some render new, and so currently we're getting two entry points, which is like the vertex shader and index shaders, but in this case the clear color function doesn't need shaders. Alright, we could make them an option though, but or honestly, you know what, we need this to be a struct anyways, Kind of like what we did with the render params. Really, yeah. I mean, sure, let's try that out, I guess. So render create info, should I call that? And then like you have, so it's basically the format, the image format, and the VS entry point, the FS entry point. Right. Though this should be optional. But then if they're optional, that means if one of them is off, oh boy. Da, 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 da. Then basically like the pipeline should be optional. Should we go that far? Yeah, honestly that would slow us down too much. So yeah, let's actually remove that. Let's remove the clear color example for now. Maybe later on we could come back to it. Right now we really need some faster velocity, and by making the abstraction I'm already slowing myself down. But here we go. Either way, so elapsed is never used. Yeah, let's remove it for now, I guess. Hasher, let's remove that. Fine. And let's go. So it only takes you 150 lines of code to make a triangle using the engine here. Cool. Now, can we try this? All right, let's actually try this. Instead of a triangle, let's try to render something more interesting. I never used this crate before, but I guess we'll find out. We'll find out if we can use it. Well, let's see. So the thing is, this crate is re-exported in Leon. So this is part of a bigger crate called Leon. Okay. So Leon is a GPU-based 2D graphics rendering tools in Rust using path tessellation. Okay. And so this meta crate, so this is just a meta crate, which means it's only re-exporting stuff. It's not an actual thing, you know, it's not an actual library that have something. It's just like essentially it's a group of libraries, right? So Leon tessellation, path tessellation routines. Tessellation is exactly what we need, I think, here. Leon path, tools to build and iterate over paths. I mean, various 2D path related algorithms, 2D utilities for cubic and quadratic Bezier curves, arcs, and more, additional testing and debugging tools. I mean, maybe we need all of them. I don't know, I'm not sure, we'll see. There is an WGPU example, that's interesting. Now the nice thing though about WGPU is that you could find like more support for it in the community, but there's some useful documentation of project's wiki. The source code is available on the Git repo. And this is an example. Tessellating a rounded rectangle. Exactly, that's cool. So the Leon tessellation crate provides a collection of tessellation routines for common shapes such as rectangles and circles. Let's have a look at how to obtain the fill tessellation a rectangle with rounded corners. So here you just say geometry, vertex buffers, new, and then you create a simple builder. Fill options tolerance 1, you create a tessellator builder. Then you add a rounded rectangle here. So basically add shapes, I believe, here. And right. And then you build the vertex buffer. And then it gives you vertices and indices. Perfect. That's exactly what I want. Exactly what I want. Well, I guess we're gonna beat Qt with this. Alright, so layout distillation. Crate. Building and tessellating arbitrary path. This one though is gonna use the path library 2 of Leon essentially. Gotcha. Let's use our own custom vertex type instead of the default one. Oh, right. Perfect. Perfect. Compute the tessellation. Tessellate path. Leon does not provide with any GPU abstraction or rendering backend. Throw out GTK and Qt. Kodateco Engine RS is future. Yeah, exactly. Let's see. The WGPU example can be used to get an idea of how to render geometry, in this case using WGPU. Yeah, so let's actually pull in this whole crate called Leon. And let's try. I really never tried it before, so we're gonna try this on stream. Cargo add Leon. And you have these features. There's also Leon Extra, which I'm not sure what it adds. There's also serialization and a debugger for some reason. And we have here an example, a WGPU example. This program renders a Rust logo, fill and stroke. The geometry is tessellated once at initialization and stays on the GPU. Some parameters such as color and stroke which width are stored in uniform buffer. There's updated every frame. Opaque geometry is drawn in front to back order with the depth buffer enabled. Oh, this is the wiki. You should then change rendering from fill to line. I'm really curious about how the Leon generated mesh looks. Yeah, we'll try that. So we'll try that. If you're interested in contributing, there's some useful info on the wiki. So there's quite a few things here, but I just want to get to the code honestly at this point. This seems very interesting. So we got an example of WGPU. I have actually programmed in WGPU before, so this should probably not be that bad. Screenshot.png. I also like to try to make, a video encoder using FFmpeg in Rust for our engine, though gated behind a feature, of course. But we'll see about that. I also work with FFmpeg, so that's a piece of cake. Globals. GPU vertex, position, normal, prim, ID. Okay, globals. So as you can see here, all right, great. So you notice this here, we're actually, like listing the vertex attributes using the offsets and so on and these weird things. This is done for us by Volcano. We don't have to do it. It's just, it infers it from the struct, right? So notice here we don't have like a, macro here, but here we do. So look at this format. So it just does it for us, which is great. The other thing, what's up? So we got here primitive, blah, blah. Honestly, you know what? Let's just try to code this. No need for, or, let me just skim through this real quick. Let's skim through this. Fill vertex, constructor, GPU vertex. Scene params. Bruh. Okay, so how much they have a vertex buffers for the tessellated vertices. Geometry. Yeah, really, honestly, I just get to coding and figure it out. Yeah. And I believe here there is the render pass, right? Where is the render pass? Wait, bind layout. So notice this is how you create a buffer in WGPU, by the way. You pass in the byte size, so there's no type here, right? It's not typed, they just bytes, which is... They also have the bind group layout stuff, which kind of suck. Volcano would also handle that for us. What else? Pipeline layout. Create render pipeline. Either way, let's get to coding really and figure it out on the way. Pretty much. Let's see. So let's start with the example I believe that is here, which is rounded rectangle, and we're gonna basically copy this code. All right, so all right, let's copy this code and see. So here where we're putting the vertices. So this is a mess. We really need to figure out how to clean this up at some point. But I wanted to do some more features first, so I could see the shape of how everything going, and then I could decide on how we're gonna abstract this out. Either way, so instead of this vertices, we're gonna generate them now using this library. Now let's import everything we're gonna need here. I don't know, whatever. Though I remember they were talking about like our own custom vertex. Yeah, you pass it here, vertex buffers here. So here's our vertex struct, cool. And we need an index buffer. We haven't made an index buffer yet, but we'll see about that. Let's import this simple builder. I'm not sure which one I should use, honestly, but whichever. I think probably they're the same. I would guess it's just a re-export or something. Yeah, it's probably just a re-export, so whichever, doesn't matter. Yeah, that's pretty much it. And let's just import everything we need here. That's kind of annoying that there's two of them. But anyways... let's unwrap this, and I believe this should basically gives us the geometry, but like wait, what? Wait, so build a path object consuming the builder, but like why we're not storing this? It doesn't return anything, so I guess it builds it in place somehow. Yeah, into this geometry builder, and this geometry builder builds into geometry. That's kind of weird. I don't know why they did it this way, but they probably have a reason to though. But either way, all right, let me try to figure out what the heck is going on here. So type mismatch, expected mutable vertex buffers lay on path point U16. Ah, I see. So let's actually follow with this one maybe. Tessellator geometry. But like why we need this anyways? So we need it here. Wait. So let's go step by step here. So we're creating vertex buffers. What is this? So this is a structure that holds the vertex and index data, usually written into through temporary buffer builder objects. But this simpler builder expects a vertex buffer's points, so we can't use that, definitely. So what should we use instead? So here builder, what it takes. Tessellate directly from a sequence of path builder commands without creating an intermediate path data structure. Well, I mean, both of these are using a fill tessellator, right? So I guess we could just steal this. Or, I'm so confused. You know what? Let's just try. Remove this, and then what? So tessellator.builder, where this is using tessellator. Well, here it's using tessellator. You know what? Let's copy this one instead. Let's copy this one. Fine. And then we could figure out how to do the other one. Okay, let's see. Mm-hmm. Use it in the color buffers builder. Import. And there we go. Now, instead of this, I think we could grab it from the geometry. I can't type geometry today. Dot vertices. Could you talk a bit about multi-threading in Vulkan? I have no idea about anything. I guess one way of doing it would be for each window to have its own thread. Yeah, I mean, you could do that, but for now, we don't really have to worry about multi-threading. It's kind of a little advanced, but yeah. Alright, so can we just pass in geometry vertices in wrap, and we're good. And then we pass that. But of course, we can also use the index buffer that it generates. But let's just try this without the index buffer. I'm curious. It's supposed to create like a Bezier path. There's something weird going on here, right? Yeah. Alright, let's see. So we need the index buffer too now. So let's implement the index buffer. Well, it's actually going to be a piece of cake, I believe. So, of course, sub buffer of, in this case, it needs to be, I guess, U16. It could be either U16 or U32, depends on the index type you want to use. Now, we're going to create another buffer. Hello, Valina. Welcome to live stream. I opened your stream for fun while playing Balatro, and it's really fun to see someone else enjoying that fabulous language. Yeah, thank you so much, Valina. What is Balatro? What kind of game that is? I never heard of it before. Just want to say a quick something. Time to go sleep. Balatro's. What? Right. Indices vector of U16, and we pass in the indices, and notice here it automatically infers that it's U16 buffer. Perfect. Now let's add the missing fields. Alright, cool. And what are we gonna do now? Now let's see, let's go down to, okay, here. So bind index vertex buffer, and let's bind the index buffer. And the index buffer is basically mesh.index buffer. And in wrap the result, And then what we're gonna do, instead of draw, we're gonna use draw indexed. Now the index count is self.index, mesh.index buffer dot length, comma 1 instance for now, comma 0. And then here, let's say at savecast 32, I believe. Value user. Oh yeah. Yes. So this should be index count, please. And then here, index buffer. Now I'm just gonna use this here. Alright. That seems to work. Now let's see if this. Yeah, now let's pass in the geometry indices. It's a card game, poker style, hard to describe. Played it for the first time, I had more fun than I expected. I'm sorry, I'm not a big fan of card games, but that's okay. I heard you talked about Factorio and RimWorld earlier. Yeah, I really love Factorio and RimWorld. Okay. Let's see. What the heck? Oh yeah. Hold on. Let's go back to where we came from. Let's see. Index buffer. Now here we need to use index buffer. This is I rarely play games nowadays. My game is usually JetBrains. Yeah, me too. It's usually JetBrains IDEs. Alright, so we do have something here. It's kind of strange though. Maybe we have to change this to a line, as Mucho said, and see how that goes. Yeah, I probably need some sort of a camera or something here though. Let's see. Where to even start with that? Balatro is an indie game that got mainstream popularity. It was nice to see. Gotcha. I never heard of that, honestly. Now, let's see how that would go. Right, where we're creating the pipeline. We're creating it in the render. Now, in the render, let's see where that goes. Maybe the input assembly state, or yeah, well, topology? No, not topology. Order rasterization. I think here. My friend said I had an IDE problem when I had both Raster over WebStorm and PyCharm opened. Huh? Wait, polygon mode. Okay, I think this one, polygon mode. But why it's interesting. Well, let's do this basically, and then rasterization state default, or too simply default. Whoops. I just understood. My brain is lagging. Let's see. Polygon mode. So instead of fill, I guess we need a line here maybe. How about that? Bruh. So we need like a device feature for this? What the heck? Requires one of device features, fill mode, non-solid. Apparently we need a feature for this. Weird. Oh, okay. Where are we creating the freaking device? Let's see. Here. Okay, and enable features here, I guess. Fill. Alright, let's turn this feature on. Alright. But we're not seeing. I mean, what that's supposed to draw anyways is supposed to draw some path. Quadratic Bezier 2. Alright, let me mess with that now. Since we're drawing that correctly, I believe, maybe. Let's mess with that. Go back here. And let's see what we got. So this is kind of like HTML5 canvas apparently. So you begin at 0, 0. Then you make a line to 1. What else we have? What we could do other than that? We could add all these. And here's the add rounded triangle that we've seen before. That would be cool. And we can see transformed and transform. That's cool. Add point, add polygon. Flattened. Alright, reserve transformed with SVG. Right. Let's try the rounded rectangle that we've seen earlier right now, maybe. Like, I guess we could try using this now instead of this thing. Maybe. I'm not sure what kind of unit is this. Probably not pixels. Yeah, I don't think it's pixels. Well, I guess we could say divided by I mean, we're getting something. We really need an orthographic camera, honestly. Need an orthographic camera. Though, what if I right now change the rendering mode to fill? Okay, we're getting this, but what the heck? This is a rounded rectangle? Huh. How do I change the... So let's see. Add a subpath containing a rectangle. There must be no subpath in progress when this method is called. No subpath is in progress. Is there a method called? Okay. Here you give it a rectangle, which is a box 2D, which is basically a minimum and maximum points, right? And a radii, border radii. Now, what I want to know is how do you set the quality of this? How do you set the quality? Well, I guess let's ask ChatGPT maybe. ChatGPT. How to set the quality of the tessellate? I believe it was called wait. I believe it was called like tolerance. I think I've seen something about tolerance, or I don't know. Let's go back real quick. There is a fill options called tolerance, but where that goes? It goes into the tessellator.builder. Huh? Wait, what? This is very confusing. All right. How about we use this instead? Okay, let's see something real quick. Now this simple builder doesn't work. Okay, what does this do? It returns a buffers builder. Oh yeah. And for the buffers builder, we had it here. So honestly, let's just buffer.vertices.len. That's kind of strange, but geometry builder. So this is your geometry builder. I mean, we could set those, I believe, to just 0 actually. Wait, can't we just say default for this? Wait. Apparently we could say new buffers. Is that really it? Provide the argument, please. Okay, so here are the buffers, which is the geometry. Mutable. And here we need some CTOR. Constructor. What that CTOR is? It's a template. Generic. Huh. How did Simple Builder did it? It used positions constructor. Well, okay. Whoops. Next up, let's make it mutable. Expected an FN fell vertex. Closure found positions. Yeah. I need to read the documentation, honestly. I need to read the documentation, really. Let's see, repository. There's examples here. Well, there's only that WGPU thing apparently. But like we could maybe figure out something from here there. Like for example, this buffers builder. Bah. Yeah, I need to read the documentation pretty much. Alright, so I think I'm probably gonna end the live stream. I'm gonna go back to the working thing that we had before. That weird rounded rectangle. Or whatever that was. What is? Let's see. So this was working, right? Yeah. So this was actually working out. Or again, as I said, actually I forgot. Let's just really ask ChatGPT and call it a day. Let's see. Let's see if ChatGPT figured it out. Alright, so how to set the quality of tessellation. And please respond immediately. The options is passed in tessellate path. Oh, it's right here. I didn't notice it. Tolerance. I'm not sure what's the default tolerance though. Okay, there you go. So we have drawn our first rounded rectangle, as you can see here. That's sick. Though right now we're not handling aspect ratio greatly. Yeah, that's so cool. Tolerance sometimes called flying tolerance to find the maximum allowed distance. Yeah, I know what it is. I just didn't see the struct where it is. Use tolerance about 0.1 units. Honestly, we need the camera, and for that, we need the uniform. Maybe we could check out some other example and steal the code from there. Let's see, wait. There's the teapot though, which actually draws a whole teapot. And what else? ray tracing. We could use push constants or push descriptors to create like a uniform buffer. Maybe actually, I think push constants is pretty easy to do this though. But we have to do some extra stuff. Yeah, honestly, I think I'm quite tired at this point. I'm gonna end the stream maybe here. Is there any questions so far? Any questions? And so I can take the time to read the documentation. That's great. And yeah, I guess maybe we are gonna work on creating the UI library in Rust with Vulkan. We're gonna be using this desolator crate and some other crates too, to make the process faster, hopefully. But yeah, this is pretty interesting. So we just got ourselves a, what is it called? A rounded rectangle? Yeah, a rounded rectangle. Okay. Let's call this just demo for now. Demo. Yeah. Demo. Wait, what the heck now? Edit. Demo. Just making sure this is working. And yeah, we've changed quite a few things, especially in the renderer. Yep. But either way, so this is our rounded triangle, rectangle, and let's commit. Well, actually, first of all, let's, commit all the changes. And just, how do you push? There we go. So we can find the source code here. At this point I'm gonna crash. I'm so tired. So yeah, you can find the code. I've just committed it pretty much. Yeah, this is what we wrote today. Alright, see you guys. Thank you so much for coming in, and goodbye.